thanks to the conveners and Ramakrishna Mission Residential College here for organizing this. So today I'm going to speak about, by the way, anybody who wants to delve into deeper thoughts during this talk, please feel free. There is no pressure. No explosion is going to happen. So I'm going to speak on explosion principles in logic. The idea is to study explosion itself, which is the negation of which, or the failure of which leads to paraconsistency. So we are going to look at explosion from different aspects. সুবিধা হবে? এটা তো দেখি যদি না here is the brief outline of the talk. Paraconsistency, as we know, and then some of our ideas. And in between, I'm also going to point out some of the directions in which the people I'm working with and myself, we are thinking as well.
Sir, you are muted right now.
So I guess people online did not hear anything I said so far. That's totally unimportant. We were talking about some arrangements about the thinking processes of people here, especially since it's after lunch. So I haven't really started the talk. So this is the brief scheme of the talk. So I'm going to talk about paraconsistency and some different ways of looking at explosion, different kinds of explosion, what explosion really amounts to, and so on. This can give us a different perspective on paraconsistency, and along the way I'll also point at some directions in which the group, the people that I'm working with, we are thinking, maybe sometimes outside paraconsistency even. So let's start. So paraconsistency is this is the standard explosion principle where we have alpha, negation alpha, just entailing everything in the language. So this is the failure of this principle is generally defined to be paraconsistency. Now there are other principles of explosion that are there in literature. So these are some examples. So for instance, you can have alpha and not alpha entailing everything, or you can have that alpha, not alpha, arrow, beta is a theorem. Every formula of this form is a theorem. And there's another variant of that. Now all of these can be proved to be equivalent in the presence of suitable principles or rules. Now there is one slightly different explosion that is there in literature. This is from a falsity constant. So this is a falsity constant is a nullity operator from which everything follows. Now what we do here in this talk, we will say that we will call this principle bot ECQ, and a falsity constant, and this constant bot will be called a falsity constant for the logic S. Now why am I calling it for the logic S? Because this constant could be exploding in one logic but not exploding when present in another logic. So it really depends on the logic. The second logic could be an extension or a sub-logic of the first one. So it all depends on the logic. Now the logic, a logic S will be called bot paraconsistent if there is no falsity constant in L for the logic. Okay, so the bot paraconsistency is just defined in terms of this constant. The bot is there in classical logic, intuitionistic logic, and other well-known logics. Usually, it has a very strong connection with the negation operator, if the operator is present. Especially in intuitionistic logic, negation is defined using the falsity constant. However, this falsity constant has other interpretations also. There are different ways of understanding the falsity constant. For example, the falsity constant can be defined as the negation of one theorem, as the conjunction of the negations of theorems, and so on. There are different understandings, basically. So we have to treat this in a different way. Now, the first step we took about 2 years back was negation-free paraconsistency. Can we define paraconsistency without using a negation operator? So we came to this obvious generalization of the explosion principle. This we are calling generalized ECQ, GECQ in short. So here S is a logic. Oh, by the way, there is one other disclaimer. I don't know if it was included in any of the previous slides, but here we are looking at things from the universal logic perspective, which means that this L need not be a formula algebra, need not be an algebra at all. Okay, usually L, when we talk about a standard logic, L is an algebra, but here we do not have any such assumptions. So L is just a set. And the turnstile relation that you see is just a relation from the power set of L to L. That's it. No Tarskian conditions assumed here. No structural conditions have been assumed. So this is the GECQ. It says that for each alpha, there is a beta such that alpha beta explodes. This is the obvious generalization of alpha not alpha entailing everything. The failure of this principle would lead to what we are calling this NF paraconsistency. So a system is called NF paraconsistent if GECQ fails in it. Fine. So now the task is to compare this new kind of paraconsistency with the standard paraconsistency and the bot paraconsistency as well. These theorems are not hard to prove. I mean, NF paraconsistency at first sight is such a strong principle. This should lead to all the other kinds of explosion failing. So the first theorem was that if you have an NF paraconsistent logic which has a unary operator, the negation is in parentheses because it doesn't really matter what you call this operator. It's just a unary operator which has some properties. And you can write an ECQ-like rule with any such unary operator. So you can call it that neg ECQ. So if you have an NF paraconsistent logic, it's also paraconsistent with respect to any such unary operator, which means that neg ECQ will fail. Then this second theorem, so if you have a monotonic logic, so see how structural rules are becoming important in some of the areas. See, if you have a monotonic logic and if you have an NF paraconsistent system, then there does not exist any phi such that it explodes by itself, which means it rules out any falsity constant in particular. So it cannot be bot paraconsistent. Now, the corollary of this is, you can see if there is a falsity constant, if it's a monotonic logic, then it cannot be NF paraconsistent. Okay? Yeah. Yeah, sure.
What about the other part? Like the normal thing I was thinking the other part. Because if something is negation paraconsistent, then that is ensuring the NF paraconsistency, right? But
No. If it's NF paraconsistent, it's very strongly paraconsistent.
Right, but that you are saying that is implies the negation paraconsistency.
No. So yes. So if it is NF paraconsistent, then it must be paraconsistent with respect to any such unary operator, which is negation-like. Because it's very easy to...
But what about the other side?
Because if something is negation paraconsistent, that means from alpha and negation alpha, beta holds, any beta follows.
You
right?
mean standard paraconsistent?
Standard paraconsistency. From alpha and negation alpha, anything follows. And this negation alpha becomes that beta.
That's a good question actually. So the first paper that we had written on this,
Right.
there we had defined a negation in terms of this GECQ principle. So
Correct.
any beta which when added to alpha leads to explosion is acting like a negation.
Yes.
But this beta is not unique. So that negation no longer is an operator, it becomes like a relation. For every alpha, there will be multiple such betas. There are examples in classical logic also. If you have alpha, any alpha, and then if you have alpha arrow not alpha, that's also a negation because using modus ponens, we'll derive not alpha, and then we have alpha not alpha. Explosion holds in classical logic, so we have beta. So therefore, alpha and alpha arrow not alpha leads to explosion. So alpha arrow not alpha is also a beta of that sort, which leads to explosion, right? So this beta is no longer unique. Now there have been some work about such kind of explosive negations. You can call it explosive negation is not right here because explosive negation means something else. You can have such pairs of formulae which will explode. So you can call one the negation of the other. But then if you can consider the class of all such formulas and somehow take a minimum or a minimal element of that class and call that the negation, there have been some work like this. But we did not do anything like that. But we defined a quasi-negation, exactly what you are saying. We defined a quasi-negation using this GECQ principle. Any beta which makes an alpha explode is a quasi-negation of alpha. But it's not unique.
Okay, I understand. Okay.
Okay, so the second problem with such a principle, we all know, we have been told that mathematicians can always define things. It's easy to define. So finding examples is the second problem. And now this came about last year. We found class of examples of these NF paraconsistent systems. Here we have to take some more structure into account. We are going to talk about left variable inclusion companions of logics. And this is something that Professor Chakraborty was mentioning about our work on the first day. So here, L is a set of formulas as usual. As it's a standard logic, so L is the set of formulas defined inductively in the usual way. You have a denumerable set of variables, finite set of connectives, the set of which we'll call signature or type. And then a left variable inclusion companion is defined in this way. So you take a logic, L turnstile, then you say that the left, you define another logic from it. That's why it's called the left variable inclusion companion. So you denote this by SL, L turnstile L, and you say that gamma turnstile L alpha, if there is a delta which is a subset of gamma, now this delta is a bit restrictive. The variables in delta must be contained inside the variables in alpha, hence the name left variable inclusion companion, and from this delta alpha follows. So it immediately enforces that this system be paraconsistent, because now you cannot derive any q, any variable q from p not p, where p is another variable different from q, because the variable inclusion makes it stop there. Okay. Now there is also another component, companion here, which is called the pure left variable inclusion companion. Now the difference I'll explain. The difference is very simple. Here the delta must be non-empty. There must be a non-empty delta. What that does is the following. In the left variable inclusion companion, see, if you have a theorem of the original logic, it will become a theorem of the left variable inclusion companion, because then this delta would be, you just take it as empty. because you have a theorem. Now, if you want to stop the theorems, then you make this delta non-empty, require this delta to be non-empty. That's the difference between left variable and pure left variable. Both of these are paraconsistent systems, by the way, easy to prove. Okay, now we can look at the relationship between NF paraconsistency and left variable inclusion. We were just looking for examples. This just came in as a surprise, but it was a nice set of examples that we got. So suppose you have a logic with a falsity constant, then the left variable inclusion companion and the pure left variable inclusion companion are not paraconsistent. Okay, and not NF paraconsistent. They're both paraconsistent, but not NF paraconsistent. That they're paraconsistent, I already told you why that should be the case. But they are not NF paraconsistent. If there is a falsity constant, which made us suspicious that is there something going on about the falsity constant? Is it somehow related to the falsity constant? So now, we started looking into it more. So the first theorem that we got is that if you have no formula, in fact no constant in your language, if you have no constant, which means there is no falsity constant. I did move. Yes. Yeah. So if there is no constant at all in the language, then the pure left variable inclusion companion must be paraconsistent. Moreover, if you just take this very benign assumptions that there is a variable which is not a theorem and or no variable is a theorem, then you can show that the left variable inclusion companion is also going to be NF paraconsistent. But that's not what we want, right? We are not quite there, because this is saying that no constant at all in the language. We want that there are constants, but there is no falsity constant. That is where we want to go. Okay. So now we discovered that we need more structure for this. So we have to have structurality. Structurality is basically invariance under substitutions. So if you have that, if L is a structural logic, if there is no falsity constant, then we can prove that the pure left variable inclusion companion is, how is this moving? Okay, so you can then prove that the pure left variable inclusion companion falsity constant is any zero array operator, null array operator, or constant in the language from which everything follows. That is a falsity constant. So if you have a structural logic, there is no falsity constant in L, then it implies that SPL, the pure left variable inclusion companion, is NF paraconsistent. Now you have to put some more assumption in there that you have at least one formula in the language that is not a theorem, then you can show that this left variable inclusion companion is also NF paraconsistent. Immediately you see that you have a huge class of examples of NF paraconsistent systems. Okay, there's another way to get the full converse. Forget about structurality. If you have transitivity, if your logic is transitive, then also you can prove a similar kind of result. So if you have monotonic and transitive logic such that you have no variable is a theorem, if there is no falsity constant, then the left variable inclusion companion becomes NF paraconsistent. And okay, so you don't even need monotonicity for the pure left variable inclusion companion. In fact, we proved in the paper that we do not need the full strength of transitivity or the full strength of monotonicity. There is only, so for example, if you have monotonicity only for the trivial sets, then also you can guarantee that this happens. Okay. Now we come to the other kind of variable inclusion companions. These are called the right variable inclusion companions. These are duals of the left. So what happens in the right? If you take a logic in the standard sense, formula algebra and so on. So the right variable inclusion companion is defined in the following way. So gamma, turnstile R alpha, turnstile R being the consequence relation of this companion, if either gamma contains an anti-theorem, which means a trivial set. It's not only a trivial set, every substitution of this gamma, or this set, so gamma contains an S anti-theorem, which means, let's say, sigma is such an anti-theorem. I'll call sigma an anti-theorem such that for every substitution of sigma, it's trivial. So not only sigma, but every substitution of sigma also explodes. So either gamma contains an anti-theorem, or the variable inclusion is just turned around. Variable alpha is contained inside variable gamma. Okay? And the pure right is you drop the anti-theorem part, you only have this. You only have the second clause, that is variable alpha is contained inside variable gamma. Now, what is the difference? The difference is you see all the anti-theorems of the original logic, that means all the trivial sets of the original logic such that every substitution of those are also trivial, those sets will pass through this filter if you are doing right variable inclusion. If you want to check the anti-theorems, if you want to stop the anti-theorems from passing through, you come to pure right. Okay. Now, the pure right variable inclusion companions which do have a negation operator, they are paraconsistent in the standard sense, that is negation ECQ, not ECQ will fail. But it's only for the pure. The right variable inclusion companions are not required to be paraconsistent. There are examples of right variable inclusion companions which are not paraconsistent. In fact, you can show for pure right, you can show this, that they are NF paraconsistent, which means paraconsistent in a stronger sense. The right variable inclusion companions, as I said, they are not paraconsistent in general, so you cannot expect them to be NF paraconsistent. So these are examples. Okay. Now, if you have this monotonicity for trivial sets, something that I have already mentioned, but here it is in front of you, that if you have this property that for any gamma which is trivial, then any superset of gamma will also be trivial. This is monotonicity for trivial sets. Now, if you have a logic which satisfies this property of monotonicity for trivial sets, then if S is NF paraconsistent, original logic is NF paraconsistent, then its right variable inclusion companion is also NF paraconsistent. Recall that the right variable inclusion companion is not in general even paraconsistent, but if you have this extra property, it is, and the original one is NF paraconsistent, then the right variable inclusion companion is also NF paraconsistent. Okay, so that is so far with GECQ. Now we have other principles of explosion. This arises from this question, sort of a naive question, that what is a principle of explosion? So if you think about it, a principle of explosion might be described as you have that allows a set, a proper subset of L to blow out or blow up to the whole set. That is C gamma of L, where gamma is a proper subset of L. That can be thought of as a principle of explosion. Okay. With that in mind, this is our next principle of explosion. It's S ECQ because it's set based. You no longer have alpha not alpha exploding. You say that for each alpha there exists a set gamma, proper subset of L, such that alpha is in gamma and it explodes. So which means that you can always take an element of L, there is a set containing the element, and that will explode. So again, it's a generalization of alpha not alpha exploding, right? But now instead of having its negation companion, you have the set. Now again, this is easy to prove that if you have a unary operator like negation in the language, then if not ECQ holds, then SECQ also holds, right? If GECQ holds, then SECQ also holds, because it's a generalization. So here's an example of a logic where ECQ doesn't hold, not ECQ doesn't hold, so it's paraconsistent. It's called Sette's logic P1. The property of this logic is that alpha not alpha will not explode, but alpha not alpha not alpha will explode. So it takes 3 elements to explode. So here you can say that this is paraconsistent. Okay, so ECQ fails, not ECQ fails. However, you can show that SECQ holds. For every alpha, there is a set containing the alpha that explodes. I mean, this is easy to see, right? Alpha not alpha not alpha will explode. Okay. Next one we thought was a little variation on SECQ. This we called SECQ prime. And this said that for every alpha, there exists a proper subset of L such that if you add this alpha to that, then it will explode. It turns out to be equivalent to SECQ. Okay, so there is nothing special here. SPECQ. SPECQ is set point. So the previous one was set base. This is set point. So for all gamma, so we now turn around SECQ. SECQ was for every alpha there is a gamma. This one is for every gamma, proper subset of L, there is an alpha which if you add to gamma will explode. Okay. Okay. Now, again, these proofs are not very hard. So if SPECQ holds in a system, then GECQ also will hold. I mean, these are not hard to prove at all. If you sit down with a pen and paper and the definitions, it's just obvious. If L has at least 3 distinct elements, then SECQ also holds in S. So SPECQ implies GECQ, SECQ. And then there is an example. So our examples look like this, which are, because it's coming from the universal logic perspective, so L can be any set. So in this particular example, maybe I should just explain one example. So this is how the enterprise works. So you take L, here L is just the non-zero natural numbers. Turnstile is this relation, and then we define this turnstile in terms of its corresponding consequence operator, C turnstile gamma. This is going to be L, which means gamma is going to explode if gamma is of this form, nn plus 1 to 2n plus 1. And otherwise, it's just not going to change. So it's going to stay as gamma. Okay. So now this example shows that SECQ holds in it, but GECQ does not. So which establishes the independence between SECQ and GECQ. Okay, so let's move on. There are a few more explosion principles that we talked about. So these are PF for point free. So far, all the explosion principles that we have discussed, they have for every alpha there is not alpha, for every alpha there is a beta, for every gamma there is an alpha, for every alpha there is a gamma, like this. So there is a mention of a point alpha. So these are point free. So point free, there are 3 different formulations that we had, 1, 2, and 3. So for all proper subsets of L, there exists a delta, which is also a proper subset, such that this delta contains gamma and delta explodes. That's the first variant. The second variant is this gamma union delta is still a proper subset of L, but that explodes. And the third variant is that for all gamma, there exists a delta non-empty such that gamma union delta is still a proper subset of L, and for every non-empty subset of this delta, if you add to gamma, then it will explode. So not only gamma union delta explodes, gamma explodes with every non-empty subset of delta. hold on to that thought. Maybe there is what you are saying is right. So then we discuss the relationships between this PFECQ1. The first variant and the second variant are actually equivalent. Okay, but the 3 is different. PFECQ3 was different. We were surprised to notice that PFECQ, where did it go? So first of all, SPECQ implies PFECQ. So PFECQ now, since 1 and 2 are equivalent, we are calling 1 and 2 just PFECQ. And then if PFECQ holds, that is the first 2 variants, then SECQ also holds. And then we had an example to show that PFECQ does not imply SPECQ, PFECQ or SECQ does not imply do not imply GECQ, and so on. Again, this is an example like that. This is a logic where the only condition on L is that it's infinite. More examples. So let's just skip ahead and come to the crux here. So if L has 3 distinct elements, PFECQ3, the third variant, is equivalent to SPECQ, the one that we saw a few slides back. SP is set point. For every gamma, there is an alpha such that gamma union alpha will explode. Okay, so then we come to this final diagram here, because these are all results of that type, right? So we come to this diagram where we have all these explosion principles mapped out, and you see the arrows indicate that one implies the other. If there is no arrow, then they're independent. Okay? So we have discussed GECQ, ECQ. ECQ is the standard sense. There is a negation operator or a negation-like unary operator, and this is written in terms of that. That will imply GECQ. This will imply SECQ. The 2 variants of SECQ are equivalent. Then we have the 3 different types of PF point-free ECQs. PFECQ1 and 2, they became equivalent. And then there's the third variant, which is equivalent to a set point. And PFECQ implies SECQ. So these are all the explosion principles that we have got accumulated in that paper. That paper already became quite large, but there are still some more principles of explosion that can be written. In fact, in that paper, we also included some partial explosion principles, which I'm not going to talk about today. Now, here is another property that is studied, finite trivializability. So if you have a logic, S is said to be finitely trivializable if there exists a finite subset of L such that it explodes. So you can see if you have a falsity constant, it's finitely trivializable. If ECQ holds, it's finitely trivializable, and so on. So if you have a monotonic logic, if S is finitely trivializable, then SECQ also holds. This is not a surprise. SECQ is for every alpha there is a gamma which contains alpha and explodes. This finite trivializability and SPECQ, we studied this relationship as well. It requires that you have this conjunction-like operator with the elimination principles of this conjunction. Then if you have finite trivializability, it will imply SPECQ. All of these, by the way, are backed by examples, multiple examples in the paper. Finite trivializability, SPECQ, if it is finitely trivializable, you have the elimination rule for the AND-like operator, then SPECQ, PFECQ, GECQ all hold in S. Finite trivializability has been studied before. So it's not anything new. We know that these logics, LP, then PAC, RM3 with the material implication, these are all not finitely trivializable logics. Hence, all of these principles will fail in these logics. Okay, not finitely trivializable, but there's an example that we constructed to show that it's possible that a logic is not finitely trivializable, but SECQ and PFECQ holds. So in other words, if you have finite trivializability, almost all of the principles will start, I mean, all of the principles of explosion that I have discussed will hold, except these two are the ones that remain, SECQ and PFECQ. Logics of formal inconsistency, I think Bidhan was talking about that. So, by the way, I promised to digress at points, I did not. So when I was talking about the left variable inclusion companions, there is something that I missed. I don't know, maybe I should mention, it's an interesting work that is developing. So this variable inclusion relation, that is a variable delta contained inside variable alpha, so we are thinking of generalizing this to any relation from power set of L to L. And then calling that relational companions. And Shayantan recently has been thinking that, okay, so if it's a relation from power set of L to L, then you can think of it as another consequence relation. And so it could be thought of as another deductive companion of this logic. So there are two turnstiles. Anyway, so logics of formal inconsistency, this is also something that that we are looking at now. In fact, Aisha, who is, I think, in the call, she's looking at logics of formal inconsistency. More specifically, she is looking at LFIs as well as LFUs. LFUs are logics of formal undeterminacy or undeterminedness. So what she's trying to develop now is a paracomplete system. So there was a paper a few years back by Walter and Juliana about paraconsistent probabilities. So she's trying to develop a work in the same line, but paracomplete probabilities. So instead of LFIs, we will have LFUs there. So so LFIs, I think I can skip because Vidhan already described this. So we got the feeling of what an LFI is. So we investigated on the relationship between LFIs and these various principles of explosion. So we found out that if you have an LFI, then PFECQ and SECQ, they will hold in S. So you can say that what we are trying to do is there are these different kinds of paraconsistent systems. Like LFIs are different from, let's say, LP or some other 3-valued or 4-valued system, or say, let's say, set as logic P1. So these are presented in different ways. So if you talk about different kinds of principles of explosion, which lead, the failures of which lead to different kinds of paraconsistency, you can probably see all of these systems in a more uniform way. One or the other kind of explosion fails, and hence they are paraconsistent. Okay, so if you have a finitely gently explosive, I haven't defined this, finitely gently explosive. Did you talk about you talked about gently explosive, right? So finitely gently explosive is that your this set will be finite. So this big circle P, which is the set of some formulas which depend exclusively on the variable P, and then from there you can define this big circle phi, where you replace the P with a particular formula phi, right? So then you get these sets big circle phi, which contain some formulas which depend exclusively on this formula phi. So the function of this big circle phi set is the classicality conditions of phi. So if you have phi, not phi, along with the set of formulas which establish the classicality of phi, then you have explosion. That is the concept of LFI. So finitely gently explosive basically just means that this big circle phi will be finite. Okay, so if you have a finitely gently explosive LFI, And then in the signature of S, you have a conjunction operator for which these elimination rules hold. Then you can prove that SP, CQ, and GCQ will also hold. Okay. And I guess that's where I wanted to stop.
Any question from the audience? Also, question from the online audience? Anyone? Sir.
No questions, but maybe considered as a comment. That part I know, this left variable inclusion thing turns out to be paraconsistent, that I know. What is new to me is this more general thing. Only I have just one sort of, anxiety. Anxiety is this: if something becomes too general, it becomes too contentless. More, it becomes general. So it should be you should be cautious about that. That's my point. I know the attitude of Sayantan, and so he wants to enter into more and more generalizations. So it is, I think, Shanko's responsibility to check whether these generalizations really become substantial. So about what you have done here, I cannot say that much. I only, because you have given plenty of examples. So you have, then the question will be what we will do with these examples, what we will do with these paraconsistent systems, what next steps you can take. That is the only point that I would like to make.
Yeah, so finding examples becomes all the more vital for any kind of work like this. So that's something that we are always working on, and I'm glad that we have this class of examples. The other thing that have come, so the paper is still under review, so it's been a year now, more than a year. So it's under review with Studiologica. So it came, we got 2 reviews a few months back, and we have already submitted our responses to the comments. One of the reviewers very rightly, I think, commented that this is an important work and it has to be seen now from the algebraic viewpoint. So what happens in the abstract algebraic logic field if you want to develop such things. So that might be a useful.
Any other question or comment from the online participants? If you have anything? Well, if not, then I think that we may proceed to the next talk. And we thank Shanko for the nice presentation. And hello? Yes. Okay, so let me introduce our next speaker of this workshop, who is Professor Walter Carnielli. He is a professor from Clay and the Department of Philosophy, University of Campinas, Brazil. And he is going to speak on Da Costa's contribution to paraconsistent thinking. So we know that he is one of the famous paraconsistent logician throughout the world, and we are very much happy to have him in this paraconsistent reasoning workshop. So it is over to you, Professor Carnielli. So you may start your presentation. So can you please check whether your screen can be shared, and then the online participants and we can see it.
Morning.
Yes.
Morning from the other side of the world. Let me try to show my screen.
Yes.
Okay. We're happy you don't see my face, but you see my screen. What's more important than myself?
So your voice is clear. Your voice is clearly audible. It is also more important. And yeah.
Okay, very
Yes.
nice.
Yes.
That's important.
Yes.
Well, let me start by thanking everyone. Thank you the Calcutta Logic Circle and the Ramakrishna College for organizing this beautiful homage to Da Costa, and especially Shurov Tarafider and Polak Samantha for the organizers. I think they are the main organizer, although many people have helped in this enterprise. I'm very pleased to say something about Da Costa's contribution to paraconsistent thinking. Here you see, can you see my slides well?
So we can see the Gmail account is open. So we can see your screen. So if you can go to the slides, you can check that we can see the slides as well.
Yeah, well, I'm already showing my slides. You can see them?
No. It's fixed in your email.
Oh my goodness, let me see. Oh, just a moment. The misters of computers, these little monsters. Let me try to tame this little monster that all the time is trying to play games on us. I don't know.
Still
just a
not
moment.
visible. So
It's not my computer, but to make things worse.
Oh.
I'm talking from very far away, not from my office.
oh,
I was using a telephone, it's not working.
okay.
So I decided to use Juliana's computer. And now she has the trouble of making the monster to work. I don't know. I think you have to close the window. Close this window.
I think you can.
Yeah, eles estão vendo essa tela aqui. Fecha essa tela, porque essa tela tá errada. Eles estão vendo o meu e-mail, tá vendo?
Sei lá onde são.
Tá no PDF. It's easy to discuss in your own language when things are going wrong. Now, okay, share this
Yes.
screen.
One
Okay.
more time, you share.
Now, okay, now you can see it. Okay, very nice. So make it bigger, please. So I have a picture of Da Costa I'm going to show you in a moment.
Yes, sure.
Anyway, I would like to thank Shonka Bashu for making my life easier. He sort of explained many of the concepts I was about to explain, so I can go more quickly and concentrate on Da Costa's contribution. And also, I'll say some friendly criticism to Da Costa's as well, because if it were not for this criticism, we would be stuck in the past. So the criticism to a master helps us to go ahead. No. No, make it bigger. It was okay.
Não sei onde é isso.
No, that's okay. No, you can see. Can you see it?
Não sei onde é isso.
No, you can see it. Can you see it?
Não sei onde é isso.
No, no, you can see it. Can you see it? Still
No,
not?
no. So it's not shared. The screen
no.
is not shared now.
It's not shared. Yeah. Before it was shared, but before you were able to see.
Yeah, before the screen was shared, but it was fixed in one screen, so it was not moving.
It was not.
Yeah. So there is a second option that you can send the slides to us, and we can control your slide from here.
Yes, in the last case I will do that.
Yes.
In the last case I
Yes.
will do that.
Yes.
But I prefer to control
Yeah,
because
sure.
if I control, I can go quickly, right?
Correct.
Tem que escolher agora o arquivo.
Yeah,
Espelho infinito. Não, pensa. Yeah, okay.
we can see it now.
Dispensa. Okay.
Yeah.
Good,
So
good.
Can you please change the slides so that we can see that it is changing here? Can you please change the slides
Yes.
so that we can see that
Yes.
it is changing here as well? No, it's not changing.
No, it's not changing. No, it's stop it. Little monster, what you are doing to us?
Probably it's too early morning. The computer is not wake up yet, I think.
Yeah, exactly. Too early. The sun is rising in this part of the world.
Yes.
So now you're here a discussion in Portuguese to make something a bit more funny. Como é que você faz para quando você vai apresentar?
Eu apresento.
Ela apresenta. Well,
Vejo se
No.
tá-
no.
Now it's moving.
No.
Yes. Yes, we saw the next slide. Yes.
Da Costa?
Yes.
Da
Yes.
Costa, and go to the next slide. Let's see whether it is
Next
working.
slide. Next slide. Yeah,
Yes,
okay.
yes, it's working. It's working. Yes.
Right.
Just a
Finally, the little monster came
Yes.
in. So this is a picture of Da Costa not so
Yeah.
long ago. He died from 94 to 95 years old, and I see this opportunity to talk about Da Costa as an honor to him and an honor to my mother, my dearly mother that died some week ago, with his age more or less the same. So they were the same age, and so I lost two personalities. I lost Da Costa and I lost my mother, and I had already lost my father. So this is life. Let's go bravely on. Let me praise Da Costa for his visionary proposal, this famous logic CN. It's really visionary, because I compare Da Costa with this Russian professor who axiomatized probability, Kolmogorov. Kolmogorov did something which was not so easy to do, to axiomatize something, probability, that seemed to be not axiomatizable, right? Even some people said by that time, well, it's impossible to axiomatize probability because it involves non-mathematical concepts like randomicity or events. What's the notion of an event? What's an event? How can you say what's an event mathematically? How can you say what's something to be randomic mathematically and logically? And he did it with 4 or 5 little axioms. Kolmogorov axiomatized the whole of probability. And Newton da Costa did more or less the same, in my opinion. People used to say, no, that's impossible. How can you axiomatize logically something which is not logical, like contradictions or inconsistency, right? So it's a brave proposal, in my opinion. His first thesis was a kind of full professor's thesis, sistemas formais inconsistentes, or inconsistent formal systems. And this little word, inconsistent, or inconsistent in French, or inconsistent in Portuguese, is going to play an important role, as I tell you in the next slide. So this is not very well regarded by his colleagues from the mathematics department or from philosophy department. They said, you are crazy. How can you do that? You don't have anything better to do? Go there, work in topology, work in geometry, do something in differential equations, but don't tell me these stupid things. However, things got changed when he published his notes in the Compte Rendu de l'Académie des Sciences de Paris, the famous journal of the Academy of Science of Paris, the CRAS. Right? So his notes were taken from Portuguese, from Curitiba to Clermont-Ferrand in France by Artibano Micali. Artibano Micali was already dead, was an algebraist, a Brazilian algebraist who worked in France, and he took the notes from Da Costa, written in somehow bad French, and passed them to Marcel Guillaume. Marcel Guillaume, perhaps you heard about him. Marcel Guillaume is a famous figure, a famous French mathematician, logician, who is famous because he invented the possible word semantics before Kripke, but he did not publish it. The paper was initially not accepted. You know why? Because inconsistent, like inconsistent or inconsistent in Portuguese, was not a French word. They could not publish it because this word did not exist in the French vocabulary before. But then Guillaume found that it was used by Poincaré at the end of the 19th century. So Poincaré helped the logical, paraconsistent logic somehow. You see, this for me is really incredible. Consider the history of the ideas of paraconsistent logic that we know very well, and then Shankar presented so nicely some moments before. So Da Costa then ended up by publishing 3 papers, everything in French, the calcul propositionnel pour le système informel, propositional calculus for the inconsistent formal systems, then predicate calculus for the inconsistent formal system, and description calculus for the inconsistent formal system. So he was using the word inconsistent all the time, although nowadays we prefer to make a distinction between inconsistent, trivial, and contradictory. And I tell you in a moment, following the lines of Shankar. So a little criticism on the logic CN, the famous family of logic by Da Costa. Da Costa axiomatizes CN using inconsistency or bad behaviorness as a definition. So he puts this A up to the ball, A like power 0, is defined as it's not the case that A and not A. So it's problematic because there are 2 negations and they behave very differently. The internal one means possibility. So it's possible something to be A and not A in principle. But then when things are good behaved, this is bad behaved. But when things are good behaved, then I see, I put in the front of this kind of possibility, this is not the case. So this external negation means it's prohibition, it's prohibited. Prohibited to be A and not A, and this is good behavior. Otherwise, A and not A is said to be bad behavior. Well, this is problematic as I studied with Da Costa since long ago, like I would say 45 years perhaps. I never liked that definition because I said, well, this is crazy. How can a negation, how can a connective have such a distinct behavior or distinct interpretations? And Da Costa, you said to me, well, I don't know, it works very well. It works very well, right? Also, the valuation semantics proposed by Da Costa and studied by Elias Alves and Andrea Loparic is mathematically sound, but does not explain contradictions. So they had a kind of a very simple valuation semantics and they proved that according to valuation semantics, they had completeness and several other model theoretical properties or model theoretical features, but I didn't like it because it did not explain anything. How can you explain by a computer supposedly. Nowadays, we have artificial intelligence, we have to explain things to computers. How can we explain to a computer what a contradiction means? How does it work if you don't have a good semantic interpretation to it? Then the logic of formal inconsistent were born by João Marcos and myself. Later, Marcelo Conilho joined us. They appeared in the horizon. They appeared in our horizon. So the logic of formal inconsistent are a kind of full generalization of this Da Costa system, right? How do they work? They internalize the notion of consistency in objective language by means of a new connective. So this ball connective, white ball, can be primitive or defined, but it means something new. It means a new connective, right? And then they separate the notions of consistency for the non-contradiction. So ball A, consistent A, is not exactly the same as to be well-behaved in Da Costa's idea. They have a connection in the sense that, as I see my third line, consistency of A implies well-behaved in Da Costa sense, but not vice versa. The converse does not hold. So in some logics, they separate the contradiction. They also separate the notion of a consistency contradiction and inconsistency, or not ball. Not ball means contradiction. In some logics, I have A and not A imply it's not the case of a ball A, but the converse does not hold. So this logical form inconsistency, they are nice because they make possible to separate several notions. So in this way, consistency is not the same as freedom from contradiction. So in classical logic, consistent and non-contradiction are equivalent notion. But the common sense says that this is not reasonable. For instance, a contradictory information about a password is not tolerable because a password is something rigid, inflexible, strict, or consistent, right? So the idea of something to be consistent seems that is rigid, inflexible, strict. However, a contradictory information about weather forecast, for instance, is tolerable because weather forecast is flexible, adaptable, or fuzzy, if you like, or not consistent. So things that are not consistent are the flexible ideas, flexible information, flexible notions, right? So information may come from a multi-source, and the sources themselves can have a distinct degree of confidence. So it's important to be able to measure how hard a contradiction can be, taking into account the uncertainty of the agents. So in this way, by using the logic of formal inconsistency, we can sort of measure how hard a contradiction can be, right? So they are, I go very quickly here. So again, they are logics that tolerate, internalize the notion of consistent by a white ball and inconsistent by a black ball. Sometimes consistent and inconsistent can be interdefined from each other by means of negation. Sometimes not. It depends on how strong the logic is. But then we can make sensible inferences in the presence of contradictions. We don't need to throw away good information or a good piece of evidence because it contains some contradiction. Okay, so in the LFIs, as I said, the notions of consistent and contradiction are not coincident, nor are the notions of inconsistent and contradiction the same. And for Da Costa, this was not very clear. That's why he called his system inconsistent formal systems and not non-trivial formal system. That would be a better name. But who are we to legislate in the past, right? So he chose that. That's the way it's going to be. So there's an infinity hierarchy of LFIs, as Shonka mentioned. 3 valued ones, not many valued, etc. CI, MBC, CI, CILA, blah, 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 blah. There are many of them. The Costa system is just one part of this big family, and they also can be raised to first order case. But I say that Da Costa was a visionary because months before the World Wide Web, Michael Dunn, more or less recently in 2018, said the following: main motivation that I see for consistent logic comes from the internet and this World Wide Web. Belknap was prescient in motivating what has become now as a Belknap done for valued logic. By the way, it is very alike, very, in my opinion, it's very similar, or it's a modern version of this Nagarjuna tetralema, right? Belknap done for valued logic by talking of an structured database in which various people might enter inconsistent data or contradictory data. I would say contradictory data because in our view, João Marco, Marcelo, Itala, Juliana, and myself, and many other people, inconsistency is not the same as contradiction. So I would say contradictory data. This is before the World Wide Web. And now, not only do we have this enormous unstructured database, but we have bots, like robots, roaming it for information, like ants roaming the web, assuming that these bots will perform inferences. I see paraconsistent logic as an essential tool to prevent the explosion in the contemporary world of the World Wide Web. Right? This is done said by Belknap. So he was referring to this famous using for valid logic, and he's talking about information computer science. So Da Costa was able to do this before there was any need, because he thought that the contradiction would be some kind of a very good point to be reasoning about, right? So what we have is the principle of a gentle explosion, which says consistent A and not A leads to an explosion. But if I have only A and not A, it does not lead to explosion. So the principle of a gentle explosion only says the following: the only modification to logic is that if something is consistent, it cannot be contradictory. Otherwise, it can be. Right? So in this sense, this particle here, consistency A and not A, works like a bottom particle, like a classical bottom particle. And using this bottom particle, we can restore classical logic again. So classical logic turns out to be a particular case of LFIs. LFIs are sort of expanding the logical realms. Huh? So the main questions of paraconsistent logic are the following: what is the nature of contradictions that are accepted in paraconsistent logic? working with a kind of reduced logic because we don't have any principal explosion anymore, or they have it just a modified and a weaker version of the principal explosion, and this makes us put on us the burden of redefining everything, reinventing everything, and we are doing. Many people are helping us, including people from India and from everywhere. Mihir Chakraborty, Shankar Bashu, other people, Shurav Tarafder, or many other people from India are helping us in this enterprise and many other parts of the world. Now, the possible translations appeared in the Horizon, and these new semantics that I had the idea to propose that, and I was working by my colleagues, João Marcos, Marcelo Bonillo, and myself. And I'll give some examples starting from a basic proposition of paraconsistent logic is MBC. MBC starts from positive classical logic, which is assumed as a and then it's a very weak logic. It don't even reach this CN system of da Costa. It's very, very simple and basic. And the idea of possible translations is the idea of working by translating a complicated logic into simpler one. I give you as a John Marcus proposed that very nice idea of Rosetta Stone, a kind of parallel with Rosetta. This kind of stone has three texts, and they say the same. Okay, we don't know anything about the hieroglyphical writing, but you know Demotic, we know Old Greek. Let's try to compare. And by comparing, by making this assumption, they found a way of understanding hieroglyphical writing from Old Egypt. Right? So I go to this first to this nice. The logic is more or less the same. You have a strange logic. We have a strange logic, and then we translate. It may even not to be many valued. I don't know. It has no noun semantic. Has no possible word semantics, no cryptic semantics, no many value semantics, nothing. But we don't know what it is. So if we try to translate it into very simple logic, like I say, like a three-valued logic, is most of the cases. If you have a bunch of translations, something like if many people understand it like a strange language, there are many people from different cultures understand a part of it. And then we compose this understanding, and we have an understanding for the strange logic. So, in the case of this MBC, we translated it into three-valued logics. We translated it into three-valued logic, which is different. So the conjunction is the same, the disjunction is the same, implication is the same, but then we have we translate it into three different meanings, into three different ways of understanding negation, and three different ways. It's enough for us. Three would be two, but three is sufficient. Two ways of understanding the consistency operator in three-valued logics. Okay, so we compose an understanding of a complicated logic into three. We partitionate it, we decompose it into three simple three-valued logics. Why I say simple three-valued logic? Because they share the same positive connectives, but they give rise to different ones by using negation number one, negation number two, negation number three, consistent number one, consistent number two, consistent number three. So for instance, consistent number one regards true as true, and true and little, intermediate truths as false, and false as true. I mean, it is consistent. So, real true and real false are translated as fairly consistent. An intermediate is translated as not truly consistent, falsely consistent, and so on and so on. So the others have the same understanding, and by composing them, as I said, we get a new semantics for this strange logic. It's a kind of simple, clever idea, I say. So let me just finish this part by appealing to Sir Arthur Conan Doyle in the Sign of Four, to Sherlock Holmes. Do not let contradictions distract you, and truth will appear, eliminating all other factors, and the one which remains must be truth. Right? It is very, very good, very clever advice to people that are trying to make sensible reasoning under the pressure of contradictions. Do not contradictions distract you, and truth will appear. That's exactly what people do in a law judgment, in a court, in science, when they have different theories explaining something. Wait a moment, go ahead, and the truth will appear. Okay, then we have a new other kinds of semantics. The one I worked with is Marcelo Conilio, a swap structure. Swap structure is a way of understanding things by looking at the triples X, Y, and Z in the swap structure refer to truth values. So what may be of this swap structure? That you take together phi, formula phi, it's a negation, and it is consistent value. So you take this triple as a new way of looking for a sentence. You don't only, because the idea is very simple. In classical logic, negation is totally dependent on the negation of phi is totally dependent on phi. If you know the value, truth value of phi, you know the truth value of negation of phi. It's not your positive way. But in this kind of complicated logic, you may have phi true and not phi true as well, or phi true and not phi false. They may behave classically or non-classically. And then, depending on that, you have the truth value of the consistency. So, if something is true, a negation is false, it's consistent. But, so consistency is true. But if something is true, a negation is true, consistent is false. So the simple idea is that you are evaluating together this triple, and this triple is said to be a swap structure. Why is it swap? Because it changes values, right? So this using this idea of swap structure, we come up with the idea of non-deterministic matrices. Huh? What are non-deterministic matrices? So it's like a three-valued logic for MBC, for instance. So MBC is not any, you can prove it, MBC is not any many-valued logic. It's not three-valued, not four-valued, not even 17-valued logic. It's not any finite-valued logic in any sense. But then working for them in a non-deterministic way, like for instance, we have here the deterministic value true, small t, another t, two degrees of truth, and one of the degree of falsity. And then you compose a table only said if something is true and, for instance, for conjunction, if A is true and B is true, then A and B can have any the D value, any of these three D values. So in this, each of these cells, it appears two or three different sets. So it has no fixed value, but non-deterministic, finitely non-deterministic value, right? Again, it's another way of working with this possible translation semantics. Only now they are aligned into a truth table. So again, the same for disjunction, for implication, for negation, and for conjunction, blah, blah, blah. So we find a 5-valued non-deterministic matrix, which characterizes MBC. Why it's 5-valued? Because it has 5 values here. D, T, big T, and really true, middle truths, a little less. So 2 different kinds, the degrees of truth, really false, and a degree of falsity. These 5 guys putting together give us a non-deterministic 5-valued matrix for MBC. Again, MBC is not many valued, not even 3 valued, not even 5 valued, but it has a 5-valued non-deterministic matrix semantics, right? So the same method holds for many logics of formal inconsistency. They are closely related to possible related semantics. So Marcelo Conilho and his students, they are working on finding something very interesting. This kind of non-deterministic structures for modal logic, for familiar modal logics. As you know, by Dugun's theorem, modal logic are not characterized by any finite metrics, but it can be characterized by non-deterministic finite valued metrics, semantics, right? So the another question that appears, the question of the algebraizability. So as we know, just for clearness, the MBC, so as I said, MBC is obtained from positive classical logic, adding tertium non datur, and adding this principle, it should be written, there's less missing here, this principle of gentle explosion, which says consistent of the alpha implies that alpha and negation of the alpha implies any possible beta. So it explodes, contradictions explode in the presence of a consistency, right? So MBC is logical formal inconsistent. And one hard problem is that it's very hard to find an algebraic counterpart for this logic because the replacement property does not hold. So if alpha is equivalent to beta, then by changing alpha and beta in everywhere, by changing every possible component P for alpha beta and everywhere gives rise to an equivalent formula again. But for da Costa's logic, saying as well for MBC, etc., it does not hold. Why it does not hold? Because you may have alpha and equivalent beta as a theorem, but negation of alpha is not necessarily equivalent to the negation of beta. So equivalent is not maintained upon negations, not even upon consistency operators. So we had the idea of a very simple idea in principle, adding 2 new rules to this MBC rule. Say the following: if alpha and beta are consistent, then axiomatically, not alpha and not beta is equivalent. If alpha is equivalent to beta, consistent of alpha is equivalent to consistent of beta. But the semantic counterpart of this movie is not so obvious. We had to work a lot. We even, I tell you, we use the artificial intelligence to help us. We use this Isabelle proof helping system. So by adding to these new rules, we changing the notion of derivation, blah, 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 I'm not going into details, we were able to find a way to give a Boolean algebra with LFI operators, we call BALPHI as an algebra, like as a Boolean algebra extended with these new operations for consistency and for negation, right? And then by using this kind of Boolean algebra with operators, as much as people do in modal logic, for instance. We have a new semantics for this MBC. We call it RMBC. In this RMBC, it's really algebraic because now we can make this Lindenbaum-Tarski algebras. We can compose an Lindenbaum-Tarski, and then we have a way of algebraizing this logic. And the same movement can be done for several other LFIs, right? So we now have a way to work in obtaining this algebraic counterpart for the LFIs. And this is very important because when you have an algebraic counterpart, like a simple, like a Lindenbaum-Tarski algebra, you can make many mathematical ideas working fine. Again, like probability, you can talk about sigma algebra, for instance, and etc., etc., etc. So first order paraconsistence, da Costa was the first to study quantifiers and paraconsistence. As I mentioned in one of his first French papers, he used that. We are now using more or less the same ideas. There's not much difference between first order version of LFIs and the first order versions of classical structures. We are talking about the paraconsistent Tarskian structures as well. The only thing that we have to be careful is with the semantics of negation and inconsistency. Always, those guys always cause new problems. They're our little monsters here. We have to take care of them. And then again, we do this by evaluation semantics. They're not the best possible solution, but they work very well. We can obtain a completeness theorem. You can obtain a compactness theorem, blah, blah, blah. And by changing the notion of inconsistency to inconsistent to non-trivial and consistent with trivial, by changing these little ideas, we can work with ranking sets and blah, 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 blah. And more or less, it's just complicated technically, but not really, a little bit complicated technically. But if you are versed in classical model theory, you can do this very easily. And then again, what do you gain for that? We can reconstruct the model theory completely, like basically all the books of model theory, all the classical theorems, almost all of them, I don't know, say all, but almost all the theorems of classical model theory can be reconstructed in this new first order logic is here, right? So you have many, like Löwenheim theorems and compactness and blah, 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 and even a form of Craig interpolation lemma, so many other results in model theory. So we arrive to new forms of that theory. So da Costa started the paraconsistent set theory, these systems NF, ZFI. NF was considered as a paraconsistent version of a new foundations from Quine. ZFI is a new form of Zermelo-Franco. So da Costa wrote this in 1986 on paraconsistent set theory, published in Logique Analyse, Nouvelle Série in 1986. But it's a very important point here. That's his main concern to paraconsistent set theory was not, or is not, according to his writing, to make it possible the existence of problematic objects like a Russell set. He was not really concerned in making possible Russell set. On the contrary, the most important characteristic of paraconsistence or set theory in general is to handle the extension of inconsistent predicates into mathematics. For instance, in the examples that he liked to give, dialecticians, the idea of dialectics of Hegel, for instance, there exists a real contradiction in the word in the sense of Hegel. He said, okay, we can model that. We don't need to assume that they are real, but if Hegel says that, we can model that mathematically. Psychoanalytic theory, for instance, Da Costa was interested in psychoanalysis, in Lacan, in trying to understand the connections between Lacan and paraconsistent reasoning, the theory of dreams and kind of psychoanalysis. Meinung is theory of objects. Meinung is impossibility objects, for instance. So Da Costa invented this kind of new sets, paraconsistent sets, in order to expand, not only in a way of helping Zermelo-Fraenkel theory or his Russell set, right? But there were some disagreements. Aida Huda and Diederik Battens, in their paper, Russell set versus the universal set in paraconsistent theory, showed that if you're not careful enough, some theory of Da Costa can be trivial. So there was some stopping in this idea. They were halting for some time. And then Cornelio and myself, we published a reformulation, new paraconsistent set theory, where we thought about using this operation of a consistency to talk just in very simple terms. We thought about considering consistent objects versus consistent sets, right? We'll be comparing the consistency of a set with the consistency of its elements. And then other proposals appeared. Now we have Shurav and other people working in new kinds of paraconsistent set theory. Giorgio is working on that. Giorgio gave a talk yesterday about that. Professor Mihir Sakaburt, working on this thing. Santiago, these people that I know. Other people that I don't remember, Thierry Libert, and the other guys. I mean, other people are already starting to work on paraconsistent theory. It's very nice and very good because this is a new development of the subject. Okay, so what Marcelo Cornelio and I, what we did was I'm not going to this, just to this axiom here that talk about consistency. So we have C and little ball, and C is a consistent operator for sets. So for every x, if x belongs to I, if a set x is consistent, so is y. So if x belongs to I and x is consistent as a set, y is also consistent. Axiom number 2, for every x, if C is a consistent set, then it's not that all elements behave consistent, but equality behaves consistent. Equality is a predicate. Predicates are consistent or not. So if something is some set is consistent, equality for objects behaves well. Otherwise, it does not. Right? Number 3, if equality is not consistent, the set itself is not consistent. So we are then comparing the consistency of sets with the consistency of equality between elements. Okay, so that's a new idea from our case to propose this new way of regarding paraconsistent set theory. We could prove that if ZM MBC, so this new logic, this new set theory based on MBC, is consistent if and only if ZF is consistent. I don't know if ZF is consistent, nobody knows. Gödel's theorem prohibits that, we know that. But then, if it is, our theory is consistent. If it is not, our theory is not consistent. Other people like Shurav, Giorgio, Santiago, and Mihir, and other people are working from set theory, starting from a completely different perspective, which I find very nice and very positive. And perhaps we are going, as I said yesterday, we are approaching the same universal truths about set theory or not. Or we may have completely different ways of regarding paraconsistent sets. Very well, very nice in either way. So, just to remind you that Cantor, as Dalben says in his biography of Cantor, Cantor used to call Vielheit, a collection that he was not very good, like a class in our vision today, but it's not exactly a class. A Vielheit, a collection which is not well behaved. He used to say, a collection can be so constituted that the assumption of a unification of its elements into a whole leads to a contradiction, so that it's impossible to conceive the collection as a unity, as a completed object. So collections I call absolute infinity or inconsistent collections. But taking his inconsistent set into account, so Cantor did not throw them away. Taking these inconsistent sets into account, Cantor concluded that every consistent set had to be power equivalent to a definitely. So as Dalton puts it, in one theorem, based on inconsistent of the system of all transfinite numbers, Cantor had succeeded in resolving several perplexing and long stunning problems set theory. So what did Cantor do with contradictory or this inconsistent set? He reasoned about them. That's the spirit of paraconsistent logic. If you have something crazy, reason, think about it. It may lead you to some nice conclusion. Okay, and in a certain sense, we, Marcelo Cornelia and I, we are basing our approach in this idea of Cantor, his Vielheit. So, just to show you, we have a book. I think many of you know this book, Consistent Contradiction and Negation, where we, Marcelo and I, we summarize sort of 25 years of paraconsistent at Unicamp. So we sort of summarize the research we have been done in the CLE, in our group. Many other people help here, so all of them are regarded in this book. I think it's a nice book from the point of view of putting everything together. So there's a hard problem is to find good models for paraconsistent theory. We have twisted valid models for tree-valid paraconsistent theory. Giorgio presented yesterday a nice new way of putting two algebras together to make it a cross product and obtaining new models. I mean, okay, this is a work in progress. Should have also worked on that. I saw that he had many papers in this kind of thing. So very nice. We are constructing and finding new models. So the thing is working again. The train is running again. Okay. So I forgot Benedict Löw and Taraf there have worked in a very nice paper, also proposing different, but they're coming from completely different motivations and reaching completely different results, and that's very positive. Let me go very quickly. Shonko mentioned already some moments ago the new forms of probability. And Da Costa himself had thought about what he called the pragmatic probabilities. He published in 1986 in the Cantonese a paper about pragmatic probability, and he has also a book in Portuguese. I don't know if it has been translated or not, named Lógica Indutiva e Probabilidade, or Inductive Logic and Probability, by Hilsetec Edusp São Paulo in 1993. And in this book, he tries to prove that induction, I mean, the problem of induction could be somehow approached from the point of view of probability in a contrary way to what Popper and Miller proved. Popper and Miller proved that there is no probabilistic solution to inductive reasoning. Da Costa thinks the other way around. Thinks that yes, there is, by means of his pragmatic probability. But Da Costa did not base his probability on systems of non-classical logic. So he was thinking about probability, but he did not, for some reason, did not think about inventing or proposing or constructing new theories of probability having as basis non-classical logic or paraconsistent logic. And that's a work we have done, Juliana Bueno Soler and myself. We proved that when you base probability on non-classical logic like CI, for instance, one of the LFIs, CI or others, or LET, logic of evidence and truth. For instance, the LET-F, an extension of the four-value down-up down logic FDE. When you base, well, we have several papers on that kind of thing, but important is that when you base your probability theory, like a Kolmogorov approach to probability theory, but starting from a basic non-classical logic, you have in complicated things like probability of A and probability of not A is not necessarily one. It can be less and be more. So probabilities can be paracomplete or paraconsistent, and then we are able to, so it can be bigger than one or less than one. The former is paracomplete when it's less than one because there will be missing information, and the other one, when it's bigger than one, is paraconsistent because there is collapsing information or contradictory information or contradictory evidence. We call it evidence, blah, blah, blah. And then we can prove that when we can talk about the degree of consistency of a proposition by means of probability, and when this alpha has, when consistency of the alpha has probability 1, then we restore classical probability. So what do we gain from that? It is, again, we are expanding the realm or the kingdom of probabilities in a sense that we have bigger theories or larger theories, wider theories of probability. And when we talk about consistency, when everything is consistent, we restore classical probability. I think it is a wonderful way of looking at the probability because you obtain new tools for reasoning, right? You obtain completely new tools for reasoning. So, especially when you're talking about probabilities for LET-F, for logic of evidence and truths based on bound-up for valid logic, you can regard probabilities as measuring the amount of evidence. You can measure evidence. You can measure the degree to which the positive and negative evidence is expected to behave classically, like in an investigation. You have positive evidence, pieces of evidence, you have negative pieces of evidence, and then you are composing them together as much as you can so that you reach truth. When the judge declares that the section is closed, he has to reach a kind of pragmatic truth in a sense. Okay? So, and then again, saying this in very simple words, we have expanded the way of looking, the way of working with probabilities, and then you can do many other things with that. You can sort of work on epistemic, for instance, Bayesian epistemology. You can work with Bayesian, you can sort of extend Bayesian epistemology, taking into account these new kinds of probability, and you obtain very nice and new results, in my opinion. I am really fond of that. So let's go quickly to other contributions by Da Costa. Da Costa started a way of working on paraconsistent deontic logic. I remember that he invited me. I was at Berkeley by that time. We were together at Berkeley. And he told me, look, why don't we work a little bit on deontic logic? I said, well, is it worthwhile? I said, yes, let's go and write a little paper on that. And then he wrote a paper on paraconsistent deontic logic, which has been published in Philosophia, a scientific philosophical journal of Israel in 1986. And then Da Costa, Carnielli, and Leila Puga, we showed that a less rigid logic than classical logic can offer new approach to deontic paradoxes or dilemmas. This contribution to the debate is recognized in this entry, Deontic Logic of the Stanford Encyclopedia of Philosophy. So I think in a certain sense, we were the first, so Da Costa and myself, and also Leila Puga as well later on, to think about deontic logic from the point of view of paraconsistent, trying to solve some moral dilemma. And Da Costa proposed also a theory of quasi-truth So along with collaborators, with Jean-Yves Bézieux and Otávio Bueno, they worked with extending the scholastic concept of truth to the theory of a quasi-truth or partial truth, which was then applied in the foundation of science. So Da Costa was convinced that science is not working with the idea of truth, the classical or the scholastic concept of truth, but they are working under a new idea that truth is sort of a quasi, in the sense that sort of a soft truth. So it's their proposal. Another contribution, Foundation of Mathematics and Physics. Sorry for this 2 centimeters, this is wrong in later comment. Da Costa research includes axiomatization of quantum mechanics, special relativity, and complexity theory. He worked intensively with Décio Krause in applications of Paraconsistent to quantum theory. And together with Francisco Doria, Da Costa and they worked on super predicates to axiomatize various physical theories, achieving significant results in completeness of the undecidability of dynamical systems. This is a very nice work of Da Costa and Doria. They show that dynamical systems are undecidable. This has to do with chaos theory. I mean, a very nice reason. I consider it a wonderful, nice reason. They worked on P equals NP, along with Doria again. Da Costa published 2 papers suggesting that the consistency of the equation P equals NP depends on Zev's third theory. So this is sort of complicated because the scientific community is still assessing them. I don't see any conclusion if this is true or not, or perhaps they have a new idea, perhaps they are wrong. But anyway, they tried. They made a nice attempt to apply the idea of consistent and inconsistent to P equals NP problem. Again, Da Costa was fond of paraconsistent annotated logics, which he considered ideal for applications. If P is propositional symbol, and P and tau is an annotation constant, P tau is a literal in the annotated logic. So annotated logic is as a kind of let's say, extending way of regarding fuzzy logic and probabilistic measures in altogether. Okay, so if you, or better, I won't say probabilistic, better possibilistic measure. I think it's better to say the possibilistic measure of Zadet, Didier Dubois, Henri Prad, these French people that work on this possibilistic measures. So in a way, this annotated logic is a sort of abstract way of thinking, of reasoning about fuzzy and possibilistic measures altogether. It's used in engineering because engineers don't care about foundations, so they only about simplicity and low computation complexity. These annotated logics they're not dealing with foundations of in any way. They are very simple logics and they're very low computational complexity, and because of that, they are very much used in engineering. Okay, so we have to say that Marcelo Conilha and I were trying to find a way of mixing these annotated logics with our LFIs, and we are making some starting progress with that. Not working on in progress yet. So what we gained from the Paraconsistent program initiated by Da Costa and continued by his students and followers, not only Brazilians, but everywhere in the world. So we gain new insights in the foundations of mathematics, new and natural set theories, extending mathematical theories, model for set theories as Cornelio, Shurov, don't have space to put all the names here, Giorgio, Santiago, and other people. New semantics for non-standard logic, like the possible translation semantics, twist structures, etc., or swap structures. New perspective on Guido's incompleteness. So that's a work I'm doing with David Fuenmayor, not ready yet, but we are trying to prove that Guido's incompleteness theorem still holds in a sort of a weaker logic, like paraconsistent logic, applications into engineering, computer science. So GPT and artificial intelligence and new ways of neural nets, etc., Bayesian networks, they all need a new way, new way of dealing with contradictions, and I think that's going to be very useful in this regard. So that's all. So I think that Da Costa really invented, that's my honor to him, he invented a new way now that are unifying many researchers in the world into a nice and new enterprise. So congratulations, Da Costa. Congratulations, all of us, for pursuing, for making his ideas going forward. Thank you very much.
Thank you very much, Walter. That was a very nice presentation, and it's time for the audience to ask some question. So here
Thank
is
you.
Professor.
Let me try to make this little monster to not to share this thing anymore. Let me see how can I
Yes. Okay. You can stop sharing. But this is the first question from Professor Mihir Chakraborty.
Okay, just a moment. Okay, now I see. Okay. Yes.
ওটা যাচ্ছে না তো? Hello,
Professor-
Walter. Hello,
Professor-
Walter. Do you hear
Nice
me?
to meet you, Miguel.
Nice to meet you.
in person.
We have not met for a long time. So,
Yes.
yeah,
Since
for a
France.
long
Remember,
time.
we met in France.
Sorry? Yeah, we met
met
last time in
in
BC. Last time.
Vichy, yes.
Vichy, yeah, last time, yeah. That was long ago. But we should meet before we pass away.
Yeah. Yes.
Meet
Let's do
again.
it.
Okay, first of all, thank you very much for this wonderful exposition of your work along with Professor Newton da Costa. And we are really happy that we could organize in a small way.
Yeah, what was
a
a wonderful
homage,
idea. I congratulate you guys. Wonderful idea.
a homage to Professor da Costa. You know, actually, we are a small group here now, but since you visited Calcutta in 2015, in the fifth World Congress, 2014, the progress in India on paraconsistency is quite substantive. So I think
I'm glad to hear that.
we thought-
I'm very glad to hear that.
and having said this, actually, I have, in fact, I don't have any specific question, just to appreciate you about informing us the multifaceted personality of Newton da Costa. And
Yes.
of course, you also are a multifaceted personality. My specific question is, did you notice any interest in Professor Newton da Costa on other fields such as art or literature or society, etc.? So I wonder if he had any, he definitely had interest, I can understand, but did he write anything on the connection between, say, not connection, his impression about the art, particularly art of South Asia, South America. If you
Yes.
could give me some information, I'll be very happy to read some of them. Thank you very much.
Okay. Wonderful questions. It's a very nice question. Yes, on this social and artistic attitude. I know that Da Costa was a conservative person. So he was very much conservative. He was interested in literature and music and many other things. But from the purely point, as far as I know, for the purely point of view of classical music, classical literature, he was not really much interested into South American literature, or as I am, for instance. I read all of them. I read everything that people do write in Spanish in Latin America, because I find it very progressive, very alive, very colorful. Da Costa was a sort of conservative person in this kind of view. He was much interested into psychoanalysis, for instance, much more than in art, as far as I know. So he was very much interested in Lacan, more than in Freud, for instance. But as far as I know, of course, he was very much, he read a lot about classical literature, and he knew a lot about history, and that, etc. And he considered himself a leftist. Politically, he considered himself a leftist, but a very conservative leftist. He was not progressive in any way. I didn't see him as a progressive person, like he worried about world hunger or social life of people. No, he was a kind of leftist in the sense of Hegel's, more or less, let's say. Hegel's ideas, right? And no, here I don't know any work that he's has done on the direction of South American painting or music, or even the south part of the world, like the global south, like Mexican or Australian or Philippines or other things like that. So no, he was not interested in that, as far as I know. But it's a nice point. I try to see. Maybe he did something. Who knows? As far as I know, he did not play any instrument, not even piano, nothing like that. He didn't know how to sing anything. But he was a very nice personality, very conservative on one hand, very much conservative, but very much inclined into the leftists. He would say he was a communist. Oh, he wasn't really a communist, because he was a sort of a middle class to rich person, not really a modest, simple people's person. But anyway, a kind of very prolific personality, multifaceted, as you say, prolific personality. Yes, but I try to see to it. Maybe he has done something in this direction.
I think in this topic, Marcos has written something, that he has some collection of poetry of Da Costa, so he may play that.
Yes, yes, I know his poetry. Well, I don't consider his poetry very much deep, but anyway, yeah, it's true. Yeah, under a pseudonym, under another name, he published some poems.
Uh-huh.
Yes, you're right.
Yes.
But I never paid attention to that, to tell you the truth.
And I think that
I may read them again, maybe.
In the chat box, Marcos has already shared a link on that, I think. So we
okay,
can,
good. Thank you,
we
Joe
can
Marcos.
play that.
Yes,
So
yes.
yeah. But before we go to that, is there any other question or any comment from the online participants, since we are running a little bit late? So any quick question? Anything else? Well, so if not, we thank to Walter for this very wonderful presentation and thought-provoking presentation, and like we discussed a lot of things. You discussed a lot of things about Newton da Costa. And well, so I think that we are not going for the break, which was in the schedule from 4 to 4:15. So it is already 4:15. So we'll directly go to Marcos' presentation. And if Marcos, if you want, so we'll invite you. When you will start your presentation, you can go to that poetry if you want, or directly you can go to the presentation. The poetry is here, so we will listen to that later. But then let me properly introduce Joe Marcos, who is from. And before that, we want just give a big clap for Walter Carnielli for this presentation. And formally, we end the topic here. Yeah. And then let's invite Professor Joe Marcos, who is from the Department of Philosophy, Federal University of Santa Catarina. And Marcos is going to speak on, the title of his presentation is On a General Theory of Recapture, How to Fix a Classically Defective Connective.
Thank you all. Thank you, everyone. Thank you, Jean Marcus, for reminding me about the poetry of Newton da Costa. Yes,
Yes.
I never paid attention to that. I will.
It's worth
Thank you.
reading, Walter. Thank you very much.
Thank you.
I do have the book somewhere in one of these boxes. I've just moved, but so I would read from the book if possible, knowing that West Bengal is the state of poetry. So I would be pleased to read if I could find the book right now, but I'm sorry I can't. I can't do it at the moment. So
But
thank you very much.
just reminding us, Da Costa was publishing under a Danish name, right? Something
Yes,
like that.
he claimed it was his cousin.
Yeah.
Called
Okay,
Lars
thank you.
Eriksson. Yes. Thank you
Okay.
very much. So, as I have been introduced and the talk is already in there, I apologize if I make you guys miss the break. It's so important.
No,
to
no,
break.
no. Please, you can start. Don't be apologized. So we are happy to see you. That's all. So you may start. I can just before you start. I can just to the audience. I just want to. Okay, Professor Meet Chakraborty want to share something before you start.
Hello, Joe. Hello,
Meet.
Joe. Do you hear me?
Yes,
Yeah,
I can.
You remember
proceed.
your ride in India? Huh?
Yes,
from
yes.
Delhi to
15
Kolkata,
years ago.
and from Kolkata to perhaps south somewhere, Hyderabad. Yeah. Okay.
Yeah.
Nice to see you again. And we remember,
very nice.
we remember
pleased
your
to be here.
hospitality. Yes. Oh, bolbe
I
ekটু?
apologize not being in person. I hope next time this is gonna happen.
Okay.
This was 15 years ago. I will remind it with a picture at the end. But I was very pleased and honored to visit Kolkata then, and I'm happy to be back, even if in a remote presentation on a general theory of recapture. So it's a proposal on how to fix a classically defective connective, and I dedicate the talk to Newton da Costa and the school that he has developed. So I start with this quote by St. Francis de Sales. I'm sure it would sound much better in Italian and even better and more poetic if written in Bengali. But the idea here about gentleness is the one that I would like us to see, how it has been implemented by this school. And I want to see how we can generalize these ideas. So let me start from the beginning, which is by fixing language for us to talk about, just a set of sentences. And what I want to consider as something to assert or deny about, or to make judgments about, is what I call a consecution, which is just a pair of sets of formulas. And the way I'm going to use this is like this. I'm going to write one set to the left and another set to the right. And when I put a black triangle in between them, what I'm saying, if you want to read the same way as I do, is that asserting all the sentences on the left-hand side is compatible with denying all the sentences on the right-hand side. So we can imagine that the task here is similar to the task of satisfiability, when you either satisfy or not a sentence. And we have these two kinds of boxes in which we can push sentences into. So the box of assertions and the box of denial. And consequence will be just the opposite of it. So I say that the set on the right is a consequence from the set on the left. So the conclusion set follows from the premise set, if and only if it's not compatible to assert all the sentences in pi, while denying all the sentences in sigma. Okay, so I'm gonna use this reading so much that you're gonna get used to it, but I'm gonna just fix it for the start. So let's go to negations and non-classical negations. How do they fit this picture? Well, let's say we have this thing that everybody has in their mind when they think about a consequence relation, but generalized, so that we have this premise set and a conclusion set, and assume that we are not discussing whether the symbol is a negation or not. Assume that for the moment it's a legitimate negation and present in the language. There are a lot of things I could say. For instance, disregarding a negation itself, if I write something like this, I'm saying that it's possible, it's viable, it's it's something we can do or consider to assert simultaneously all the sentences in the language. Some logics do that or allow you to do that, like logic LP. And in that case, I'm going to say that this logic admits a Dadaistic reading. So everything could be right. Everything could be asserted simultaneously. Dually, you could also consider the situation in which you can deny everything. I call it a nihilistic approach. And if I want to have a classic-like negation, I would like to say some things about negations, to fix, for instance, that I shouldn't assert a formula in its negation, and I shouldn't deny simultaneously a formula in its negation. So asserting one of these things commits one to denying the other if we have only these two kinds of judgments in the language. Now, paraconsistency can be seen precisely as a way of trying to escape that predicament and saying, well, why not asserting a sentence and its negation simultaneously, as long as you don't assert anything else or everything else? So you are committed to the possibility or to the compatibility between the acts of asserting P and not P while denying something. Obviously not P and not P, but something. And paracompleteness could be thought as being the dual approach. So you're committed to denying some formula together with its negation while not denying everything else, so asserting something else. And we could define paranormality as being the behavior of a logic that's either paraconsistent or paracomplete. And as Avram and others have defined recently, paradefiniteness is the behavior of a logic being both paraconsistent and paracomplete. I'm going to rewrite this so that we can read it more easily. So instead of writing all those symbols, we can just say what I just wrote in now. And the principle of explosion is going against a logic or a negation being definite, in the sense that if this holds, so we cannot have this part, the left part of the definition of negation being definite. So we're failing to have a classical negation. And there's another way of failing, which is a way pursued by intuitionistic logicians or constructive-like logicians, which will deny the other part of the definition of a definite negation or classic-like negation. I call it the principle of implosion here now. Now, the thing is, we lost classical logic, and we might have good reasons to miss it. So can we restore what we have lost? So in a sense, we can say that paraconsistent logics, what they do in a very general way is to fail what we call the classical consistency assumption, to use the terminology of Diederik Battens and his group. And while the paracomplete logics, the dual logics, will fail the other assumption, the determinateness assumption. Now, to give an example of how the consistency assumption affects the logic when it fails, we can consider very important inferences such as disjunctive syllogism or contraposition. Now, once we have the possibility of asserting a sentence P, and we have kind of a standard disjunction, we are probably willing to assert also P disjunction something else. Now, if we also assert not P, then there is no reason to say that Q should be asserted as well, because this disjunction could be asserted because of P rather than because of Q. So in that case, disjunctive syllogism, which is a very important and ability survival that we have when we have two choices to make and one of them is not available, is no longer for us to use. And that's obviously a big miss, a big thing that's going to be standing out as being lost when we go into this kind of models or this kind of logics. The same way, if you assert not P, then if you have a standard implication, you're going to be willing to insert this irrelevant not Q here and assert this implication together with possibly asserting P. And there is no reason in that case to conclude that Q should also be asserted. Now, this these special inferences have been pointed out repeatedly in the literature by, for instance, Lewis and Langford for disjunctive syllogism or Popper for contraposition as being things that we should be willing to not to stick with if we're going into the direction of losing the consistency assumption, so going into the direction of having a paraconsistent logic. And this has been pointed out since the beginning of the literature in the area by Yashkovsky, da Costa, and many others. Now, how to recover it? As I was saying, maybe what you would like to do is that, well, we have this defective negation, this negation which is not classic-like, but maybe there is another one which has a classic-like behavior. So instead of having disjunctive syllogism for the native paraconsistent negation of your crazy logic, you might want to have a way of recovering it by using these other negations. So if you have this other negation around, maybe you can just recover just the way you had before and say, yeah, if you want to have disjunctive syllogism, don't use that negation, use this one, which is the one that behaves nicely with that respect. The same for contraposition. So by way of a translation, you could try to find inside a non-classical logic a fragment that behaves classically. Now, another way of recovering, which is the one we're going to focus on, is just leave it as it is. You have this negation which is non-standard, but maybe you want to select the models, you want to select the situations, you want to say that, well, perhaps P and not P cannot be simultaneously asserted as long as you know something else about P, namely that P is consistent. So the idea was to internalize the notion of consistency at the object level language so as that you can recover the lost inferences of classical logic by adding this extra assumption. Now, this is what we're going to explore a little bit more closely. I'm going to show you that this gave origin of what's now called the derivability adjustment theorems. So you don't have the inference you had at the beginning, but you have an adjusted version of that inference, as long as your language is expressive enough to have consistency connected inside it. So you go that, you see that I'm going towards introducing what Walter has already mentioned, the logics of formal inconsistency, where this can happen. So the environment is you're inside a paraconsistent logic. So I'm saying that here you fail explosion. I'm adding some other symbols here, which I'm going to use later on, especially this one, which is a white ball, which is going to be used to express consistency. So the idea was to introduce a new notion of explosion, which is a careful version, a gentle version, in which rather than saying that you cannot assert P and not P, you say that you cannot do it as long as you have information about P behaving well. So that's the good behavior that da Costa introduced in the literature. Also, there are some other things you might want to say is that this new consistency connective, it's allowing you to say that this P behaves consistently, but it's not playing the role of negation. So you might have a formula P being consistent and a formula not P being consistent. And you might want to have a little bit more. You might want to have this behaving classically. So I call this basic or standard version of the connective, when something else is also valid. Maybe this is hard to read, so let me just rewrite this in this way. So being gently explosive means that both P and not P may be consistently asserted, while if you assert P and not P, then P is not consistent. So you should deny the consistency of P. Now this is an if-then, and if you want to have the converse direction, then you need this standard version of the connective, which I put in here. So the symbols that I wrote before, basically try to say and try to explain what it means for consistency to be captured at the object language level and captured in a standard or stronger way, which is not in the original definition of the logical formula consistency as we will see, but it's an interesting thing to have. Now, if you have a consistency connective, you might want to have an inconsistency connective, which would be behaving in the opposite way. So you assert inconsistency if and only if you deny consistency. And the logical formal inconsistency was defined precisely as being any paraconsistent logic, which turned out to be gently explosive. So it turned out to have this kind of unary connectives in the language. Now, if this might sound artificial to you, it's interesting to point out, important to point out that many logics in the literature, even if they didn't come already associated with this connective, they allowed for the definition of this connective. So there is something there that we're capturing by writing it down explicitly and pointing out what it does, which is what we're going to do at the moment. Okay, so that's in general terms what a logical formal inconsistency is. This was a crash course in 10 or 15 minutes to explain to you what this is, and that's it. So you have a non-explosive negation, you have a unary consistency connective, which allows for explosion to be recovered. You might notice that I'm starting to use now a new symbol for negation because I want sometimes to have one kind of negation or another kind of non-classical negation. And I use a smile to talk about the paraconsistent negation, just like I use the frown to talk about the paracomplete negations. If you have trouble reminding it, remember that smile is connected to us in the South, is connected to the global South, is happy people. The frown is like these people living in places where it's always raining, they have their heads down, they're sad, like intuitionists. Okay. Now, we don't have to go into this. I just want to flash that C systems, which are very common terminology in the literature, they were defined, they were recovered as a particular kinds of logical formal inconsistency built in a certain way, in a specific way. And these systems, as the first systems proposed by da Costa, they actually were able to define the consistency connected using the resource or the expressive means from the object language. For instance, the favorite formula of Newton da Costa, which was the negation of phi, conjunction not phi, could be pointed out as some way of expressing the so-called principle of non-contradiction at the object language level. We don't need to express it like that. That's just one way of doing it. And if you go towards that, you get logics such as the logic C1. Now, what's more important for me here is to look at not how ubiquitous, because I tried to convince you that this is everywhere in the literature. Actually, most paraconsistent logics can be reformulated as logics of formal inconsistency, but what we can do with them. So that idea of recovering what has been lost. So let me dwell on this for a moment, if you allow me. So let me introduce something else, which is quite useful into explaining how all those symbols relate to each other, which is the so-called square of oppositions, or a modern version of the square of oppositions. And instead of formulating it with negation or whatever, let me just put it in terms of conjunction and disjunction and nend and nor, okay? So if you write it like that, you can even be more specific. You can take one rule, one inference characteristic of conjunction, and you can talk about the dual version of it, the contradictory version of it, and the antonym of it. What does that mean? Well, in one case here, it's not compatible to assert two sentences and deny the conjunction of those two sentences. While here, you change assertions and denials, and it's no longer compatible to deny a disjunction, to assert the disjunction while denying the two parts, the two components of that disjunction. So these two things are the conjunction introduction and the disjunction elimination are dual rules. And the connectives are also dual because each rule of each connective is dual to a rule characterizing the other connective. And if we put the negation in front of the conjunction, as we know, we have an end. And that's what we have here. We have a rule saying that, well, it's not compatible to assert P, Q, and NAND of PQ. Okay, same thing over here. This will be the contradictory version of the disjunction elimination. Now, what do we do with that? Well, basically, what I want us to do is the following. Imagine that we could put in one of these corners of the square the consistency connective. What do we put in the other corners? So it's very easy if we do the classical connectives. But what if we come with this new connective we have no intuition about? Well, for one, the first easy thing we can do is that we can talk about the contradictory version of it. So the classical negation of it, if we have classical negation in the language, and the opposite of consistency, as we have already introduced, is the inconsistency connective. Now, one might ask what is in the other two vertices of the square, which is reasonable. And as I explained up here, what we have to do is to look at the inferences. We have to do is to look at the statements characterizing that connective to understand what that connective is about. So let's do it. So if we look at the upper left corner, what we find here and here and here in these three positions is precisely the definition of a consistency connective and the definition of gentle explosion. Now, what do we find then here? Well, that's the inconsistency connective, as we have already mentioned before. And if we do the same things that we did here for conjunction and disjunction, namely just pushing things from left to right, from right to left, changing connectives by their duals, we have things like this. So what is this? Well, this is saying that whatever this dual of the negation is, and whatever this dual of this consistency connective is, one cannot deny simultaneously the three things. So if you deny P and the negation of P, whatever that negation is, one should mark this down by saying that, well, then this is the case. What is this? Well, this is the situation in which something is going wrong. So you're marking undeterminedness. You're marking the situation in which you have both a formula and its negation being denied. That might be something the paracomplete logician would be happy with. So this is precisely where the undeterminedness connective lives. And here, which is the classical negation of it, is where the determinedness connective lives. So the four new connectives that appear in the other slide, they relate to each other in this way. Rule by rule, you can create one of these connectives by starting from the other and following the rules of the square. Okay, so these are the this is the basic versions of the connectives. And as I said, you could have the standard versions by adding the converse directions. I'm not going to write them down here. Just wanted to try to convince that these things are related to each other in a structure called the square. Now, let's see what happens then when we have all this in a square. Let's focus just on the four connectives that we have here. So the idea, as I said, is that we have, say, consistency here, and the dual of it is undeterminedness, while the contradictory version of it is inconsistency, and the antonym of it is determinedness. Now, I'm assuming that we have a negation in the language, and it might well happen that you have two negations in the language. So these connections might break as long as we're not talking about a single negation, but about negations which are quite different from each other. They might not relate to each other the way we want. But in case they do, in case we can say that the smile is the dual to the frown, everything goes fine, and we have this structure here where everything fits together with these new restoration connectives, which is the kind of thing I want to pursue in a general sense. So we're talking about a situation which is of interest to us here, a workshop on paraconsistent logics, and I want to go beyond. At the moment, what I can point out is that if I had a classical negation in the language, these would all be very simple to explain, because contradictoriness is the external negation, antonymy is the internal negation, just like in the tradition from the Aristotelian diagrams, and duality is what we usually do when we do De Morgan rules. We put a negation inside, a negation outside. Now, it might happen that the square collapses, and instead of having four different positions, we have a single connective playing the role of both consistency and determinedness connectives. This happens, for instance, very easily if you go into four-valued logics and you look for one connective that fixes it all. In that case, this connective is going to be self-antonym, and the square is going to become a line. Okay, now, I want to introduce this important mechanism that we have, which is the derivability adjustment theorem. And for that, I need this whole language to be working. So I'm not going to point out, it's not so important at the moment, but there was some confusion in the literature about how to write all this down. Let's try to focus on what I mean by the theorem. The idea is that we can now recover inferences from classical logic inside a non-classical environment by adding new premises or new alternatives in the conclusion. So the idea is that if you have a logic in which everything goes fine, the logic in which everything is consistent, everything is determined, in that logic, you might want to say that sigma follows from pi. And now one asks oneself, what happens if you go away from that logic so that not everything behaves the way it should? Well, perhaps you can just add directly at the language what you need, just like we did in the case of disjunctive syllogism and contraposition, to recover this inference. So the inference is here, and what we need to recover it is to know that some formulas behave consistently, some other formulas behave in a determined way. So as long as we know that, we add these new premises, then we can recover the classical reasoning. Okay, and we can do it also at the other side using the contradictory versions of these connectives. It's the same. Let me give you an example to make this more maybe evident in terms of a kind of a semantical readings. But instead of using zeros and ones, true and false, I'm going to use thumbs up to say that things go well, and thumbs down to say that things don't go well. So the general picture is that you want a negation, but you don't know if it's classical. So you don't know if thumbs up goes down or thumbs down goes up, because it might not behave classically. But then you talk to a classical logician and he says, you know, about thumbs up, what I would like to have is that the negation of thumbs up is thumbs down. And the way I'm going to set it down is saying that, well, once you assert a certain formula, you are committing yourself not to asserting this, because this says that it's not a compatible position of yourself to assert simultaneously both. So the classical logician is saying that he wants to put a thumbs down here as the output, the functional output of thumbs up. But then you say, well, okay, I'm very tolerant of a classical logician. I'm going to at least allow him to have what he wants, but perhaps not in a functional way. Perhaps this is not the only thing that you can have. So I'm going to allow him to assert a formula while denying its negation. So I'm going to allow this position, but not force it. Okay? And this is going to say that this is the minimal thing that I want to impose on negation to make it a negation, to have a legitimate negation. Now, once we have that, we have another option, because we didn't force thumbs down to come from thumbs up. There's also the option of having thumbs up coming from thumbs up. Well, in that case, you would have a model, you would have a situation in which both a formula and its negation are asserted. And that would make the paraconsistent logician happy. You say, this is the situation I was talking to you about. This actually happens in the world. You're allowing me to do it while you have a legitimate negation, because you're saying that what the classical logician wanted to do is at least possible, is at least available to him or to her. Now, if I want now to have an adjustment, if I want to write this derivability adjustment theorem I had before, I need to introduce this new unary connective that's going to fix everything up. So it's going to say that when you assert P and not P, you should not assert the consistency of P. So this is what it's saying. The consistency of P, when you have both thumbs up for P and not P, is thumbs down. Okay? Now, if I add the converse, this is also telling me what happens in the other situations. So logician doing logical formal inconsistency, he's at least committing himself to that part of the meaning of the consistency connective. And if he wants it to behave in a standard way, he's also committing himself or herself to the what happens elsewhere, saying, well, okay, this is the only situation in which you have inconsistency. In all other situations, you have a consistent behavior. Now, if you want to be a classical logician, you're going to say that never happens, okay? You're creating this out of the blue. This doesn't exist. I'm going to postulate that formulas behave consistently. So that line that you had created with thumbs up and thumbs up doesn't exist. You throw it away. So that's the result of adding consistency as a new assumption. It's written in the object language, is ruling out, going against, abandoning the non-explosive behavior which the paraconsistent logician wanted to at least allow. So that's the position of the classical logician. Now, if we are in a language, we're in a logic in which, okay, some sentences behave consistently, but not all of them, then we cannot go together hand in hand with the classical logician. We need a more tolerant reading, and we need that possibility to be there, and we need the consistency assumption to be out. We need the explosion to be ruled out together with it. So in that case, the variability adjustment, as I said to you before, would be a logic in which you have things behaving consistently. So whenever you have that something follows from something else, you can always recover it by adding inside the paraconsistent logic a certain number of consistency assumptions expressed in the language, and then you have it back. Now, one might not want to add this explicitly to the language, and one other solution that has been explored was to say that, well, assume that it's already in there until and otherwise, until someone proves you that it cannot be there. So you do a non-monotonic reasoning on top of the logic. So that's why this theorem was actually, for the first time, formulated in the context of non-monotonic logics. Okay, now, how do we actually give meaning to these new connectives? We have these new 4 different connectives. I said that they fit well together. There is this square relating them, but people have given them several different names. They say these are operators of normality, classicality, recover, adjustment. What I usually say that what's behind all these approaches is that there was some ideal behind all this, which was the classical ideal. You might hate it, you might like it, but it's an ideal. The ideal was a classical idea of meaning for the classical negation, and it has been lost. This perfection of classical negation has been lost, if you want to put it like that. What I mean by perfect, this is the Aristotelian reading of perfection, in which you have all the requisite parts. It's complete. There are other readings, which also Aristotle mentions himself, which is the completeness in substance, is that nothing of the kind could be better, or completeness in purpose. One could also argue about this, but what I'm talking about when I'm talking about perfection here is something that falls from item 2, which is item 1. It's something that has all the requisite parts. The requisite parts for the classical logician is to have a negation that behaves following the consistency assumption and its dual. Okay. Now, if you lose it, one might complain, and rightfully complain, that we don't have a real negation around, but I have argued that we can give some legitimacy conditions for that negation. And these things that help us recover what has been lost, one can ask about what kind of meaning they have by themselves. And that's the first way people try to explain the meaning of those connectives. They said, well, let's think that we have this bivalent reading of everything, either things are true or false. And what we're saying is that if a formula phi and its negation are both true, then this formula is not consistent. It's false that this formula is consistent. Now, I don't like this very much. I think this is not very informative. It works technically. So if you have this kind of bivaluations, you can give semantics to paraconsistent logics, but it doesn't seem very extremely informative. So what we're looking for is some kind of other kind of models, and that's why I introduced these judgments to understand what's going on in terms of assertions and denials. The standard version would be not just an if-then, it would be an if and only if. But again, you're explaining things in terms of this classical notion of truth and falsity, and it seems that this doesn't capture all the way what's going on. Okay, so maybe, and that's what I thought at the moment, is that the whole theory is not really about classical negation. Maybe the whole theory is about losing the perfection you lost of whatever classical connective you had to start with. Because you might disagree with any classical inference characterizing any connective. So what would be then a way of writing down what this recovery consists of? can we recover whatever we lose when we look at a classical connective and say, here is a point in which I differ from the classical logician, and I want to allow new kind of model, just like the paraconsistent logician did one day for negation. So let's introduce a new connective, which is the two-valued connective. I don't really care about what it is. What I'm interested on is that it's not unary. If I manage to convince you guys that you can do this with more arguments than one, maybe this can be generalized for any number of arguments. Let's imagine we have this binary connective, and we focus on what happens in this particular cell, in which you have the two input arguments being false. Okay, so you want to know what happens in there, but you're still undecided. You don't know if you want this to be like conjunction or disjunction. In that case, this would be F. Or if you want this to be like implication or by implication or NAND, and in that case, this would be T. But then the classical logician comes and says, I know what I want. I'm not going to tell you what this connective is because I'm worried only about this particular input. But what I want is if P and Q are both true, are both false, then this particular combination of P and Q is going to be true. So he still didn't tell you if he's talking about implication, by implication, NAND, NOR, because they all agree in putting true in that position, right? So being a tolerant person, you understand what he's asking for. He's saying that he doesn't want to assert two sentences and, to deny these two sentences and also deny this combination of two sentences. So he wants to forbid the F to be an output there. He wants T to be an output there. Now you say, okay, fine. So what I'm going to give you at the moment is the following. There is a possibility that you're right. It's available to you to assert P combined with Q while denying P and Q. So you give him the possibility, but you don't tell him that this other possibility is not around. You just say to him, yeah, it's legitimate what you're saying. So this is what I'm going to allow you. And then you say, nice, but I want to be able to say what you want. I want to give you conditions to recover what you have possibly lost. So he wanted this, not allowing for the denial, simultaneous denial of P, Q, and the combination of P and Q. And you say, fine, this is okay, as long as you know something else about this connective. That you know that when F and F is an input, this connective behaves in a consistent-like way. Okay, so you say this is the connective that's going to allow you to do what you want. Whenever you can prove that about P and Q, then your connective in that particular situation behaves the way you would like it to behave. But you have to add something. You have to have this extra information explicit somehow. Okay, just copying it here, easy. We can also push this A to the other side as we have seen in the square, and you have an inconsistency-like connective. And you can determine also the other connectives. You can explain what they are in terms of the table that we had before. So you can have a connective for the other two corners of the square, as long as you dualize the connective you had from the beginning. So you had a connective that was worried about T and T. Now you have a connective that's worried about F and F, and this connective is going to be worried about T and T. Okay, so before the guy wanted to a condition so that T was at least possible in this part of the entry of the truth table. Now in the dual connective, F is going to be possible in this part of the truth table, which is it's available to you to assert P and Q while denying the combination of P and Q through that dual connective. So what we have was this. It's similar to what we had before in the example that I explained to you guys. We started with this corner, and from this corner, which was already useful to recover what the classical logician wanted, we could also determine this corner, and we could also look at the dual worry that the classical logician had at the beginning and determine the other two corners using the dual connective of that one, that whatever that one was, for that specific rule of that connective. Okay, so going back here, assuming that we don't satisfy what the classical logician wanted, so assuming that indeed I fail to have this rule that the classical logician wanted at the beginning, I'd not only say that I can recover it by adding some stuff to the set of premises, but I also need, as we needed before, a certain set of coherence conditions, which are conditions telling you that, well, these three things together cannot be denied as soon as you have that information on the left. But perhaps you can deny two of them. You can deny P and Q, you can deny P and the combination of P and Q, Q and the combination of P and Q. You just cannot deny them all together. You can deny two of them, but not all of them together. These are going to be the so-called coherence conditions. And if we want the standard versions, remember that the converse direction of the meaning of the connectives to be established, you have to add further conditions. Okay, this was the binary example, and it seems to be very general. Let's try to apply this recipe to the unary case. What comes out of it? Well, now in the unary case, imagine you start with a connective and you're undecided to what comes out as output when the input is true. Okay, so what you want initially, as a classical logician, you want maybe to say that if the input is true, the output is false. So this is what the classical logician wanted about negation. Maybe this is another connective, not negation. Maybe this is the connective that's always false. But at the moment, this is what he wants to enforce. The way we did it before, we said, yeah, fine, this is your goal, right? You want the explosion principle. Yeah, that's what I want. Okay, I'm going to allow you at least to obtain your goal, but not to force it. I'm going to allow you to have a model, to have a situation, to have the possibility of asserting some sentence while denying this connective applied to your sentence. So this is at least available to you. So the false of a true entry is available to you, but it's not forced onto you. Perhaps the other possibility is still around, which is what the classical, the paraconsistent logician wants. So in that case, what we have, following the recipe we had before, we want some connective which, when put to the left, allows us to recover the goal that the classical logician wanted. So the goal is here, and we add something to say that when that is present, we can recover that goal. We can have what the classical logician wanted. So that's the consistency-like condition. The coherence condition associated to those connectives are the important things which were there when I defined the gently paraconsistent logic, as also saying that, well, what you should worry about is to have all this being asserted simultaneously, but perhaps you can assert two of these things instead of the three of them together. Now, if you look at the other corners, you see that I'm putting in red what I'm interested on here, but automatically when I produce this, I'm producing three other things. I'm producing something here which will be the opposite of the classical opposite, the contradictory version of that connective. So that consistency connective is going to be paired with an inconsistency connective. And we are also producing things on the other two corners that we have already seen before. And the standard versions are also available and given by the recipe that I explained before, coming from the binary case, which applies to any n-ary case. So now that we just applied the recipe, which was quite general and unrelated to paraconsistent logics, what we obtain here in red is precisely the definition of gentle explosion and the standard version of gentle explosion. And you all knew that. So this is how these things, if I can rewrite history, have been obtained as more general or more specific versions of a more general theory of how you can recover what you have been lost and how you can recover what the classical logician sees as perfection. Okay, so this is what I wanted to present. I end up with this picture that I took in India 15 years ago. The word comes from Portuguese. This is in Goa. And it means that I miss you guys so much. And I hope that next time I'll be there with you. Thank you very much.
Thank you. Thank you very much, Joao, for this very interesting presentation. Now the session is open for some questions from the offline and online participants. So, any question from anyone? Yeah. Okay. So Karniali has said that has given some emoji, like emoji, I think. Yes.
Yes, I may say something. I may say something, João. Congratulations, a wonderful talk. I mean, when I heard you talking about that, but now this time is even better. It reminds me, it's a beautiful picture. It reminds me of Hermann Hesse, you know, this famous book, The Glass-Beatles Game, when you have a big picture of something very nice and wonderful and universal. It's really beautiful. I think you should write a book about that.
Thank you very
You
much.
should write a book.
Thank you
And
very
you
much,
gave
Robert.
so many contributions to the ZFIs and to the, now you are making a big picture. So just an important point. Let me, or it's not important, but a nice point. You gave the name of a gentle explosion. Remember that?
Yes.
And I think you had in mind the national anthem. No, from the soil, from the people and the soil, you are the gentle mother.
Yes.
Am I right about that?
No, you're not 100% right, because, as I said, St. Francis de Sales was what motivated me. But I had in mind that this was in the anthem, yes. But as any anthem, or most anthems in the world, is a bellic piece of literature. And I'm a pacifist, so I wouldn't mention the anthem as a motivation. But it's interesting that it mentions this gentle mother. And maybe I'm closer to the mother now in finding what was behind all this. So it's what I've been looking for many years. And I think that this position, taking the position in which you can see other things as being particular examples of a more general construction, might be useful towards understanding what's going on. So this is all towards understanding, which is what I think we should be striving for.
But I think you definitely should write a little booklet, like name it something like the Square of Perfection.
All right. I think not of the name. Thank you.
Very beautiful.
Well, any other comment? Okay, Professor Chakraborty here.
No, wonderful talk again, actually, as expected. But actually, this use of square of oppositions and that diagram is quite unique, and I think that it will. I don't know whether it has already been presented in Jaib's Bajou's one of the conferences or not. If not, I request you to present this there. Okay, I would ask about this upper arm. What is this this thing?
Yes.
What is that?
Thank you very much. I'm going to explain. So I did present this in Rome in the Square of Oppositions when it happened in the Vatican a couple of years ago. But indeed, it's not published. So I've been using this without actually presenting this in separate. I use it in other places, but I didn't present it in separate. But I think it's interesting in understanding a general theory of oppositions. So what the red part, everybody understands. The red part is the contradictory version of the square, which is the classic-like negation. So the upper part, the green part here, as you are asking for, it's the way of doing the internal negation, right? You have the external negation, which is the red part, and the internal negation is the green part. So let me just here. When you look at this line here, I call it the relation of antonymy, which is what the difference that you have, say, in natural language between being big and being small. Small is not exactly non-big, right? You have these couple of things standing in opposition to each other in language. So that's the kind of opposition we're talking about here when we go from left to right or from right to left in the square. And if it's hard to understand what it means, you can also think or pretend that you understand what duality is, which is also something very interesting to focus on, which is the blue part. And the green can always be explained as doing first blue and then red, or doing first red and then blue, right? So this is the approach by, who did this first? Before Blanchet, there was a paper in which, it fails me at the moment, in which these three kinds of opposition were explained in terms of a group, in terms of the symmetries of a group, in which you can recover one by using the others. And this is what I'm using here as a motivation. Gottschalk is the author.
Walter Gottschalk, yeah.
Yes.
Okay. Thank you. This reminds me of a recent paper by a very young student. Okay, I don't say of mine because he worked with me definitely, but he worked with me, but
Yes.
he's not a formal student of mine.
All right.
But he is going to present a paper in the upcoming conference on diagrams.
Ah, nice. That's a nice point too.
Where actually he has picturized two kinds of negations. One is the internal one, and the other is the external one. I mean the standard one. I mean the internal one means I mean what he has done is this. It is the term negation, like say non-P type, and the other one is it is not the case that. So it is similar to what here in your picture, where the negation goes inside, and on the other hand, here. But of course, these are not negations. In your case, these are not negations.
Yes.
Okay, thank you very much. But this is just one information. This paper, I think it will be, it has been accepted and it will be quite nice. My question to both of you, Joe, Marcos, and Joe and Walter, it is not question. It is my feeling. This most probably I have already mentioned earlier to either both of you or some of you or somewhere else, that this is the following. This internalization of what is an outside meta concept is something which must have some philosophical justification. We know that there are some problems and philosophical problems. Obviously, conceptual problems are there, but there are also some serious philosophical problems of internalizing metalogical concepts. For example, concept of truth. If you internalize concept of truth, you are getting this liar paradox kind of things. So, whenever you do this, the notion of consistency or inconsistency and other things, or other what are the determinacies and indeterminacies, etc. You need some extra justification, not just this formal thing. Extra justification, philosophical, I will expect some kind of formal, philosophical justification that no serious philosophical problems will arise. So this is just my comment. Most probably it is already there in your understanding and in your writings, which I have not encountered, but maybe you can say one or two words in this
Yes.
respect. Maybe Joe and even Walter, I don't know. Maybe Joe
Yes,
first.
I will start, and then Walter can also say, thank you very much, Mihir. These are very important observations and questions. For the first part, what you mentioned, the square, what I like most about this revised version of the square is that it's not, doesn't have a direction, right? The duality can go either from bottom to top, top to bottom, or vice versa. So things can be reversed. Rather than the original version of the square. And definitely share with me the paper you mentioned. It's certainly related in understanding the idea of a term negation and an external negation is in many places in the literature. So this is one way of understanding what's going on. And I'm sure that this work is related to some of the ideas I presented here. Also, I failed to mention, but there are other interesting generalizations and ideas coming from India, such as this recent work by, more or less recent work by Professor Sankar Basu and Roy Sayantan on generalized versions of explosion, which I didn't take into account here, but this would also allow us to generalize some of the things that I have presented. But the second part of your question is rather, well, okay, we do all these generalizations, we do all this symbol, play with symbols, but it must have a meaning, and we should be wary that this is not going to take us into some problems when you start putting meta-linguistic or meta-properties at the object language level. Well, for one, what I can say is that there are many advantages of doing that in many areas. For instance, when you are in modal logics and you try to internalize the notion of satisfaction at the object language level, you go into hybrid logics in which you can actually mention the worlds in where things are happening, and then you can express new properties such as irreflexivity of frames you couldn't express in modal logic. So you make the language more expressive and you can do things you couldn't do before. Now, the same happens here. So there is the advantage of doing it, which is that you can do things you couldn't do before. But as for the criticism that maybe this is putting you in a dangerous situation, I could also point out to the classical logician. He is already in that dangerous situation because the classical logician believes in this language that he can prove the consistency of the formulas. He actually works from the assumption that there is such a kind of an axiom forcing things to behave consistently, so that in that case, he wouldn't need to add consistency assumptions because they are already there. So why is it that he's allowed to make that assumption and we're not allowed to be more careful and take it out and see whether there are situations in which we can talk to him and recover his assumptions very carefully, very gently, if we're sure about it? Now, what I have been heard as a criticism about this is that this is not the role of the logician. Maybe the logician shouldn't be the one to add these assumptions and say, yeah, I can prove it. I can prove that this behaves consistently. But as you see, what I presented here contains no proof of consistency. It's an assumption of consistency. So if we can assume that it's the case, then we can recover what the classical logician already does, because he actually believes he can prove it. So in that case, the person who is in a difficult situation and who is putting herself in a dangerous position is the one who actually is, without telling us, assuming that he could express this operation, this connective at the language level, but he doesn't need to because it's a theorem. So he puts it there, he proves it, and then he doesn't tell you that he had put it there. So it was already there in that sense, and he had already assumed that he could say things about it. So he's the one saying things about it. I'm just saying that whenever I can say something about it, then I can recover what he would say because he already assumes that he has it. So in that sense, I think that we are in a very comfortable situation because we're not making those assumptions. We're just working with the possibility of them being present. Walter, you want to say something?
Yes, I would like to say something. So this is I think it's a formidable picture. And it says, in my opinion, everything about symmetry, right? is symmetry. It's like a big group of symmetry, a big topological picture of symmetry. But I think Mihir is right. Mihir is right that we need some justification from philosophy. Before that, I think we need a big justification from language, because this has always to do with the way we human people reason. For instance, when we see an orchestra, like which is not tuned, we say, well, it's not tuned. It has some inconsistency in tuning, but there's no contradiction there. Or in painting, in colors, we see, well, some colors don't match, but this is a kind of incoherence or inconsistent, but there is no contradiction. So then we see a difference between inconsistent and contradiction, as well as going to negation, we see a distinction between negation and denial and things like that. So the language itself is full of subtleties that we should be studying and perhaps noting and studying more deeply, and that is going to give us a reason to think, to construct this big picture. And after that, we go to philosophy. But I think that before anything, you have to go to language, because language is the sister of logic, right? That's my opinion. And reasoning, human reasoning, is full of the subtleties that should be sort of formalized by the big picture João Marcos has in mind. That's my idea.
Thank you very much, Walter. I failed to mention negation as this crazy way that the classical logician had of internalizing denial at the object language level. So he does it so easily, and he or she allows himself to do it, and everybody allows her to do it. And we have been living with it without asking her for a justification for doing it, because it seems so dangerous to change truth for falsity and vice versa. But that's what she needs to do to explain what negation from language does.
Thank you very much. I just say one more thing about your recapture. Okay, this is a point of attitude. Generally, it happens that when somebody grows older, he or she wants to recapture a little bit of what he or she has done earlier and come back to some old things. You are not that old. And on the other hand, I am still a person who do not want this recapturing. So this is the attitude part. And so I do not find much justification, much reason of the formalism that you have developed for recapturing. You understand my point, perhaps?
Yes, I understand.
Yeah.
Yes.
What we'll do with that is my point, and why will at all will be doing that? This is my question. Okay.
Thank you very much. So as to the age, I'm not growing any younger. So I turned 50 recently. I know it's not much, but time is passing also on this side of the Atlantic, and I hope it's somehow is going to save me when I get to the time also of making my recapture or my recollections on life. Now, I didn't say that I wanted this to happen or that I was interested in recapture. What I tried to show is that there is some technology for doing it. Once you might, in case you might want to do it. Now, the other thing I might argue is that actually it's already there. I'm just showing how it looks like if you want to straighten things up and if you want to show that it's present. But once you take a classically defective connective for whatever reason you want, and you might be willing to choose that defect to be one of negation or any other connective. Once you have it, it will happen, and that's an objective thing, it will happen that your logic can recover what has been lost, or it might happen that your logic cannot do it. So what I'm doing here is a theory to show in what situations your logic can do it. Now, if your logic was not made to do it, but it happens to have the expressive means to do it, then you are already doing it, like it or not. For instance, if you take Yeshkovsky's discursive logic, D2, which appeared 15 years before anything that da Costa thought about, 15 years before the notion of good behavior was around, 15 years before you had the idea of writing, recovering classical inferences and so on. If you look inside that logic, you see that you can define a consistency connective. So it's already there. So in that case, it's gonna do the same work that the explicit consistency connective has in the logics in which were created to have it from the start. So one thing is not wanting to have it, and the other thing is not having it, right? So for the logic that have it, that have this kind of restoration connectives, like it or not, by design or not, then the technology is gonna apply to them the way I try to sketch here. They're gonna behave this way, and in this case, you might even find beauty in recovery. You might find it interesting because then you find a way of making these two guys talk to each other, the standard one and the deviant one. They actually have some common means of communication, so can talk to each other as long as they can express certain assumptions, right? The classical logician sometimes doesn't express his assumptions explicitly because he doesn't feel the need for them, but he's making them. Okay, so the other thing is that you might not want really, and you might design your logic not to have this kind of things around, but then your logic might have other defects. For instance, your logic might allow for Dadaistic or nihilistic readings of the sentences. So if you take a logic like LP, in which you cannot express a consistency connective, you have a model in which all the sentences are true. Now, you might like this model or not, but it's there, and it's what justifies actually saying that the logic doesn't have a consistency connective. It's less expressive than many other three-valid logics which do have that connective. Now, I find it perfectly justifiable that you might not want to have it. And also find it perfectly justifiable that you might not even worry about all this, that you want everything to behave classically. Okay, so I'm just trying to develop a language so that these guys can all talk to each other.
Okay, all right, thank you. Saurabh, we have taken lots of time from you, and now Saurabh.
By no means, thank you very much.
Any other question from anyone? Any quick question from the online participants also, if anyone wants? Well, if not, then we thank again Marcos for this wonderful presentation, Corneli also for staying with us. And yeah.
Great pleasure. Thank you very much.
And thank you both again for being with us. Well, now before we end, I just request Professor Mihir Chakraborty to speak about 5 to 10 minutes if you want, and then call the session a formal end.
And it's really a pleasure to see you all, our old friends, and see all of us here, most of us of Calcutta Logic Circle here, rather many of us here, because in this area particularly, not everybody is working. So a section of members of Calcutta Logic Circle really doing this. working in this area, so not everybody is present, but definitely some who are not working but have some interest in it are present. So that is why this audience is not the full, you are not getting the full audience of Calcutta Logic Circle. But I thank, first of all, both of you, Walter and Joe, and others who delivered lectures online, and also, in fact, those who are working in this area in India, particularly the Calcutta group, Delhi group, and Kanpur IIT group. When I say group, it just means that more than one person is there. It's not a big group always. But we are happy, really happy, that it has spread at least a little. And when we were actually planning this this meeting, some of us, most probably Shankho was telling me that like Brazilians, we think that gradually from this workshop onwards, these people interested in paraconsistency will grow in India also, and there will be a substantive mass of researchers like the Brazilians now. I say that the Brazilians are Brazilians, and it is really, when I visited you, it was really a very wonderful experience. First of all, because it is South America, and second, because South America is definitely different, absolutely different, at least to me. And secondly, the thriving logic group in South America was actually an excellent inspiration to me. And we know, all of us know, it was how difficult to develop the logic group here right from scratch. Anyway, so I recall those days on this occasion, and I hope in future we will be able to. Of course, now there are these ICLA and ISLA, you know, these conferences. Besides these two conferences, we have the Calcutta Logic Circle conference also. This one is not Calcutta Logic Circle conference, but a part of it extra. We wanted to pay homage to Professor Newton da Costa, and that is why this extra program was organized. But it has been nicely done, and nicely done because of primarily the efforts, the main efforts are given by three of us. One is Saurav, other is Shankho, and third is Pulak Samanto. Pulak Samanto is a professor of this institute. He doesn't work in this field, but he has taken the absolute load of organizing things. The hall, the food, the management of this screening, etc., everything. So I think that he should be given a the highest, what? Something. So Pulak is here.
Highest recognition.
Highest recognition, yes. Yeah, it is really, in fact, what we are planning, the next CLC, Calcutta Logic Circle annual conference will be organized here in this venue. And again, we will depend on him. And I also thank the other people here. We have our friends who have actually taken trouble to organize this, what is it? This presentation, etc. So that we can see you and you can see us. So there are how many people? 2, 3 people are here. 6, 7 people. And I thank them for helping us. I also thank Ramakrishna Mission Institute of Culture, not Institute, Ramakrishna Mission College, residential college. Here there is a good news that the mathematics department, of which Pulak is a faculty member, the department is going to, has already introduced logic course, a full logic course here. This is quite something, and most probably the pioneering one, and I think in future other colleges in Kolkata or in West Bengal will also introduce the logic course. And lastly, I want to see all of you again personally, and I hope we'll get a chance to meet you somewhere. Thank you.
Thank you very much. Thank you all. It was a pleasure.
Thank you.
And
Thank you.
all.
Excellent initiative.
Thanks for the organization, and thanks me here for promoting logic in Kolkata and in India.
Thank you. Thank you. Thank you very much. So by this, we call the end of this session and the end of this workshop. So see you again. See you all. See you, everybody. See you.
See you. I see Soma there.
Thank you.
Yes,
Bye-bye.
Shoma is here. Shoma,
I wanted to say hi to Joe because
Yeah.
but didn't get chance. So yeah, good to see
Who
you.
is there? Who is speaking? Excuse me?
Soma,
দেখতে
Soma
পাচ্ছে
Duta.
না?
Soma Duta. Okay.
কোন দিকে?
Big pleasure, big pleasure.
Yeah, so I wanted to say hello to all of you also for a long time. Good to see you here.
Very, very good, Soma. I hope you're doing well.
Yeah.
Soma Duta, you almost came into Brazil for a postdoc, right? Remember that?
But I am now too old for a postdoc. It's true, yeah, I have applied and I also have visited Natal, Joe's place. So it was a really good time. Spent some time on discussing on different things. Yeah, but then I am lost somewhere in the globe.
You're still in Poland?
I am now living in Poland for a long time, almost 10 years. Dealing with machine learning, data science, logic is somewhere with my only one student, this Vidhan Shah. Maybe one of the presentation was there today in the morning. So little bit attached with paraconsistency, but not much.
Fantastic. Fantastic.
Very
I hope we
nice.
see each other in Poland.
Yes,
and-
I hope to see also like Professor Chakraborty and all, also hope to see you again sometime, somewhere
Yes.
face to face.
Certainly.
Bye.
Very nice. I will be in Poland the next year as well, in Torun.
So,
maybe we
please,
meet there.
I am living there. If somewhere nearby, let me know. It would be very nice to meet. And in any case, I think last year, Professor Diderik Battens was somewhere in Uj or somewhere, so I wanted to, Torun or somewhere for some conference, and I invited him in my university and also in Warsaw University. So it would be really very nice. If sometime some of you are nearby, please let me know.
Okay, very nice. With good pleasure.
Bye.
Okay.
Bye.
Bye.
Bye all.
Bye-bye.
Have a nice time. Have a nice
Bye-bye.
weekend.
Bye-bye.
End of. Bye bye.
Bye-bye.